Welcome to the official podcast of the NASA Johnson Space Center, episode 18, Mars. I'm Gary Jordan, and I'll be your host today. So this is the podcast where we bring in the experts, NASA scientists, engineers, astronauts, bring them right here on the show and talk about all the coolest parts about space. So today we're talking about Mars with Doug Archer, which I feel like is a good topic to bring up now because next week NASA is launching a brand new podcast called Gravity Assist. Hosted by Dr. Jim Green, NASA's Director of Planetary Science, the show will focus on planets and the solar system and beyond. So if you love planetary science, definitely subscribe to that show. It's going to start with a 10-part series on our solar system that starts with the sun and goes all the way out to Pluto and beyond. I know I'm pretty excited about it. So as sort of a taste of what you're going to get on Gravity Assist, Doug Archer will talk about the fourth planet from the sun today on Houston We Have a Podcast. Doug is a planetary scientist at the NASA Johnson Space Center here in Houston, Texas. And we had a great discussion about the red planet, what it's made of, what it's like on the surface, and why it's such an intriguing place for humans to visit in the next giant leap. So with no further delay, let's go light speed and jump right ahead to our talk with Dr. Doug Archer. Enjoy.
T-minus 5 seconds and counting. Mark. Launch commit line circle correct.
Here she goes. Houston, we have a podcast.
Yes. So you're a planetary scientist. That's your title, right? Planetary scientist.
Yep.
So I'm guessing it's exactly what it sounds like. You know the science behind why a planet is the way it is, why it's a planet and how it works and all that kind of stuff. And your specialty is Mars.
Yep. Yeah,
Sweet.
I've been working on Mars for about 13, 14 years now.
Wow. So what was it that originally fascinated you with Mars?
So like lots of kids, when I grew up, I was interested in space or being a pilot or something like that, or an astronaut. But then when I was, I think, 16, I read a book called The Case for Mars, The Plan to Settle the Red Planet and Why We Must. And it was written by a guy named Bob Zubrin, and he laid out this whole architecture for how we would get to Mars, the rockets that we would, or the type of rocket that we would need, what the habitats would look like, how long it would take to get there, just this whole architecture of how we would get to Mars, and then ultimately, like the long-term goal, right, is turning Mars into a more Earth-like place. But that's like the super long-term goal.
Right.
So this book came out, again, I think in 1996 or something like that, and there was this big cover article in Newsweek and other magazines. It kind of made big news, and I just read the articles, read the book, and just got fascinated with the idea of human exploration of Mars, and then learned more about the planet Mars. And when I was an undergrad, I was trying to figure out what major I wanted to do, and what I wanted to major in, and I was thinking about, well, I think I'm kind of good at this, and I'm kind of good at this. But what I was really passionate about was Mars and Mars exploration. And I didn't know how to make a career of that because where I went to undergrad at Brigham Young University in Utah, we didn't have any kind of space-related program there. So I just majored in physics. I found a professor who was similarly interested in Mars, and another professor in the geology department who had actually done...
At Brigham Young?
Yeah, at
Okay.
BYU. There just happened to be a few other kind of space enthusiasts there, or
Cool.
Mars enthusiasts. So they kind of pointed me on the road. And so I took an Introduction to Planetary Geology course as an undergrad and just loved that. And they pointed me on the course of, all right, here's some courses to take to prepare for grad school, and this is where you should apply. And one of the places that I applied was the University of Arizona, which has one of the few programs in planetary science in the country, or one of the few PhD programs. And I got accepted and started there in August of 2004. And the reason that I went there is because they had just won the contract from NASA to do the 2007 Mars Phoenix Scout mission. So I got to see, so I went in, and my advisor was the principal investigator for that mission, so kind of the boss over the whole mission. So I went in as a first-year grad student and worked on the Phoenix project right after it had been selected. And so my career as a grad student spanned the right after selection, all of the design work, verification, all of that for Phoenix, and then landing, surface operations and then doing the science on the stuff that we learned on the surface. And the mission ended in late 2008. So I just had this walked into this great opportunity of getting involved in an actual Mars mission as a graduate student, and just loved working on Mars, loved the mission operations aspect of it. I mean, one of the most exciting times in my life has been the 2 times when I've been able to remotely witness a robot landing on Mars, and just the absolute thrill that is, the 10 to 15 minutes of, okay, this is it. This is gonna, everything comes down to this moment, and then the thrill of seeing the first pictures from these landing sites that no one has ever seen before. Like, it is just an absolutely amazing experience to see these pictures coming in for the first time from another planet, and just having that feeling of discovery and exploration.
I can imagine, because I mean, you have such a passion for it since you pursued it so far, getting a PhD in planetary science, being fascinated with planets, and then being able to work on learn from a robot that was actually on the surface of another planet.
Yeah.
That is crazy. That is awesome. So that makes me think, why... So, your specialty is Mars, and that is a huge part of NASA's journey to Mars, right? We really want to put boots on that planet.
Yeah.
But why that planet? Obviously we have Venus, we have Titan's looks pretty cool, Enceladus. What is it about Mars that's so intriguing?
So as far as the boots, it all kind of comes back down to the boots on the ground aspect that you're talking about. Like, Titan and Enceladus are very interesting places. Europa, there's other really cool places in the solar system, including if you're looking for life outside of Earth. There's other places that you can go look. Mars is the planet that is the most likely to host life where humans can actually go. Like, we are years and probably decades to centuries away from being able to safely go to Enceladus or Titan or Europa or whatever with people.
That's pretty far away.
Yeah, we have the technology to get us to Mars, and I think that we know that in the Martian past, Mars was a lot more Earth-like than it is today. We don't exactly know how that happened. It's still an open question as how could Mars have sustained this warmer climate. For various reasons that we could get into.
Yeah.
So we don't exactly know why that's the case, but we know from geologic evidence that Mars was warmer and wetter in the past than it is today. And we know from Earth that pretty much as soon as life could have existed on Earth, it did. So we don't know how life originates exactly, but again, from Earth, we say, hey, just as soon as the conditions were right for life to exist, we find evidence of life. We know that those same conditions existed on Mars. So the question is, can we go to a place where we can find evidence of more likely past, but potential present life on Mars? And then as far as the astronauts will allow you to do a lot more science than robots will.
Right, because so we talked about this in a previous episode with Bill Foster about space communication and how difficult that's going to be. If you get a signal to Mars, it's going to take 8 minutes up to 40 minutes round trip to do anything. But if a human was there, they can make decisions rapid fire.
Yeah.
You can get a lot more done in a shorter amount of time. I'm guessing that's like pretty much the basis of why humans are that much better. Probably also the observational aspect of it. They can
absolutely
find cool parts.
Both of those things together.
Yeah.
So I'll give you an anecdote to show you kind of the limitations of robotic exploration. And first I'll talk up the benefits of robotic exploration. First of all, it's something that we can do today, right? We've been doing it on Mars now for over 40 years, where the Viking landers landed in late 1976. So we have a lot of experience at operating robots on the surface of Mars, and they are very capable. Like, the rovers can hold a lot more stuff than astronauts can. They don't have to continually go back to the hab. You don't have to send food. You don't have to worry about oxygen.
Right.
So it's a lot simpler. However, robots are only as smart as the humans that program them.
Right.
And because we have no capability of repairing or fixing something if it goes wrong, we're very cautious about how we operate the rovers, or robots. And as you said, we have this communication issue built in that makes it so that, a lot of people think that when we're operating the rovers on Mars, it's a man or a woman sitting in a room somewhere with a joystick in front of a TV, kind of, driving the rover.
Right.
But at its closest, Mars and Earth are, there's a 4-minute one-way light time delay between Mars and Earth.
Right.
So 8 minutes round trip. And at their farthest away, it's about 20 minutes one way or 40 minutes round trip. Mm-hmm. So you can imagine, anything that you're seeing is delayed by 40 minutes. So there's no way, in the worst case, 8 minutes, best case, there's no way that you can do any kind of real-time operations under those circumstances. So what we do is we plan a whole day at a time. So during the Martian night when the rover is asleep, we're awake planning the next day. And when the rover wakes up, the first thing it does is kind of check in with Earth and get the instructions for what it should be doing that day. Mm-hmm. And then it will go through the whole day of planned operations and then go to sleep, and the process repeats, wakes up. And so it sends back the data of what it did that day. We look at the data of what it did, how things went, and then plan the next day. So because of our conservatism, because we don't want to break anything, and because the robots are only as smart as we make them, mm-hmm. you'll have funny instances where, for example, the Phoenix lander, which we knew had a very limited lifetime because it was in the northern polar region, so at some point the sun was going to set and not rise again for 6 months. So, there's nothing that we could have done to make that mission last for years. We knew that going in.
Because how cold does it get when the sun sets?
When the sun sets kind of for months at a time, it can get down, I think, to like minus 130, which is the frost point for carbon dioxide. So the Martian
Fahrenheit?
atmosphere, Celsius, sorry. But at that point,
Celsius.
they're relatively similar. So the Martian atmosphere is 95% carbon dioxide, and it gets so cold that the atmosphere starts condensing out onto the surface as dry ice. So our lander, after at the end of the Martian winter, northern winter, was buried under a meter of carbon dioxide ice.
Okay, so no coming back from that.
Yeah, so we took pictures with a high-resolution camera around Mars, and it looks like one of the solar panels, which is kind of the size of a kitchen table on the lander. It had 2 panels about that size, and then the lander itself was about the same size. Mm-hmm. And it looks like one of the solar panels was broken by that. So we knew that there was almost no chance that we were going to survive to the next year. We knew that going in.
But the polar ice caps are they're super interesting. That's why you sent it there, right?
So we were just south of the permanent ice caps, but so there's the seasonal cap of CO2 and then water ice as well.
Cool.
But then the reason why we chose the location to send Phoenix is that we saw from orbit the signature of water underneath soil, and we went to confirm that, and we did. We in a few ways. One was just during the landing process, our thrusters that we used to land safely blew off the covering of the soil or loose dirt right underneath the thrusters, and you can see this ice cemented ground. Then we had a robotic arm to dig down and found that depending on exactly where we dug, between 4 and 15 centimeters deep, we found this ice layer where in a couple places it looked like it was almost pure water ice, and most of the area that we uncovered was ice cemented soil. So you could imagine taking a dish full of dirt, adding water to it, and throwing it in the freezer. And at these temperatures, or at the Martian temperatures that I was talking about earlier, it's as hard as concrete.
Wow.
But just
really hard to dig then, probably.
Yeah, so we couldn't dig into that. The best we could do, we could kind of scrape along the surface and collect what we scraped, but we also had a drill that could drill about a centimeter into the ice, and then we'd collect the tailings that came from the drill.
Okay.
But to get back to the human exploration point, one day on Mars, we're digging with the Phoenix lander, and so what you do, right, you say, okay, dig here and then dump here. So dig, in this area that we define, and then dump off in some other area.
On the surface, right?
All on the surface.
Okay.
So the arm is digging, and it goes to dump, and it just so happened to choose a path between the dig location and the dump location that there was a rock in between it that wasn't a big rock. I mean, it was, maybe 8 to 10 centimeters across, not a huge rock. Mm-hmm. But so on like the very first scoop, and it was supposed to be supposed to scoop for a while. On the very first scoop, it grabs a scoop of dirt, hits the rock, and just stops because it doesn't know what to do, right? And then we didn't program it to say like, oh, okay, well, if you hit a rock, then try this other path and
right. The only thing it knew was okay, you go from here and you go to here. It wasn't expecting an interruption. Yeah. So that's the kind of thing. So and then you go in the next day, and you see that wow, things didn't go as planned. We only have this one tiny little scoop. There was supposed to be a whole trench there. What happened? And you go look at your telemetry and say, oh, we hit a rock, and it wasn't even a very big rock. And that's the kind of thing where, for a human, right, like, oh, I hit a rock. I'll slightly move my hand and go around the rock. Right. And you don't waste an entire day from hitting a small rock. And we encounter stuff like that all the time because, again, the robot's only as smart as we are. If we encounter something unexpected, the conservative approach is usually to say, okay, just stop, and we'll tell you what to do tomorrow. So, a human doesn't have those kind of limitations. As you're saying, we have the observational ability to, first of all, analyze the landscape and say, those look like the most interesting places to go investigate. Let's go there. And then you can go do things very quickly. So the pace of exploration with humans can be a lot faster. Now, the cost is also a lot higher. Sure. So you've got to figure out kind of what's your science return per dollar. But the pace of explorations with humans can be much, much faster. Right. So, like as another example, the Curiosity Rover or the Mars Science Laboratory, which has been on Mars now for almost 5 years. Wow, that's right.
We have driven just over 16 kilometers, which is a long ways. But for a human in a human class rover, that would probably be a good day or two of driving. Right. Now, we've done a whole lot of science along the way, so you can't, it's not just, we landed and we've been doing nothing but driving.
Hit the gas pedal and just go for
5 years. Yeah. But just to give kind of a sense of scale, like I think the Opportunity Rover relatively recently surpassed how far the Apollo astronauts had driven on the moon.
Wow.
And I think so it took Opportunity over 10 years what the Apollo astronauts did in like 3 days.
Right.
So you can see that there's this difference in scale of kind of what you can accomplish. And it's interesting that you'll find that a lot of people who have experience with robotic exploration actually operating the rovers, many of us are big proponents of human exploration because we understand the limitations, because we know just how much more we could learn and how much more we could do with humans there.
Yeah. So I'm guessing. So as a planetary scientist, I guess we should have addressed this a while ago. But you, do you pick the locations where the rovers are going to go, and which rovers are you kind of working with now? Are you working with Curiosity?
Yeah. So right now I'm working with Curiosity. The only other rover that's currently operational is the Opportunity Rover,
right?
Which is amazing. It's been going for more than 13 years now.
Yeah. Way past its expected.
Yeah, the prime mission was supposed to be 90 days. So, they're like 4,000% of lifetime or something. I forget the number, but yeah, awesome. Much longer than they ever expected, which is just great and a testament to the engineers that built the rover. So I work on Curiosity, and the way that the landing site selection process works is it's a fairly democratic process. They'll have multiple meetings for years in advance of launch for scientists to come, and you can propose to land wherever you want. You can say, well, okay, within reason. So the engineers will say, okay, for this lander it needs to be within 30 degrees of the equator or 45 degrees of the equator or whatever, and you have to be able to fit a landing ellipse that's this size, and so the landing ellipse is the area in which you are confident your lander is going to land. So you'll say for the MER rovers, the landing ellipse was like 100 kilometers long and I don't remember, 15 kilometers wide or something like that. So you'd have to say, all right, you have to find a place where we can safely land anywhere inside of 100 kilometer wide or long ellipse by 20 kilometers wide. And MSL, because we got better at guidance and during entry, the landing ellipse was only like 12 kilometers long, I think, and a few kilometers wide. So a factor of 10 improvement over what we'd done before, which opened up a whole host of other landing sites.
Because now you don't have to worry about things being in the
Yeah,
way.
you don't
in
have
that
to-
100-kilometer kind of.
Yeah, you can pick a
ellipse.
lot more interesting places because your safety requirements are relaxed from just kind of the physical geography standpoint.
Mm-hmm.
But so given those restrictions, you can propose anywhere you want.
Mm-hmm.
And you go and you advocate, you make a presentation, and you advocate for this particular site and why your site is better than any of the other ones, the questions that we're going to address by landing there, why this site best meets NASA's goals and the goals of the planetary science community. And so, I mean, I think they start out with a list of like 30 to 50 landing sites or something like that. And over time, it'll get narrowed down to usually around 3 or 4. And then what happens is there will kind of be like a community consensus around, this is our top pick.
Mm-hmm.
So that's kind of the democratic side of things.
Mm-hmm.
But then ultimately the decision is made, I'm not exactly sure who, but program officer level, NASA headquarters level, where they'll say, because sometimes the scientists will pick things that are like, this is really interesting, but it's a little bit riskier than some other site. And, for the scientists, we say, yeah, we want to do it. And NASA headquarters might come in and say, guys, it's a lot more important for us to land safely than to answer this particular question.
Right.
So we're going to choose this site. But for the most part, it's very democratic about, basically anybody with a good idea can submit a candidate landing site, and then it gets talked about in the community for years. You analyze it for safety. We actually use our orbital assets that are around Mars now to take a lot of pictures of it to make sure for safety reasons that it's safe. Like another little anecdote with Phoenix, we had 4 candidate landing sites, and the top, I'm almost positive if I'm remembering correctly, the top we had decided on one landing site of, hey, we think this one's going to be the best, and then we had the high-rise camera get to Mars kind of right at the tail end of this process, so we didn't have the high enough resolution, we didn't have as high a resolution pictures as we do today. Mm-hmm. So high-rise, one of its top priorities was evaluating these potential Phoenix landing sites, and this one that we had decided was going to be our top site, the principal investigator of the high-rise image instrument, which is also built at the University of Arizona, where the Phoenix lander was. So the PI of high-rise was a good friend with the principal investigator of Phoenix, and he sent him an email with the picture of this landing site, and it was filled with massive boulders that were just below the limit of resolution of this other camera, and it would have been an awful place to land. So at that point, okay, all the other arguments are thrown out because it's not safe.
Oh yeah.
And so we went to, I think, Plan B, and they imaged that one, and it was like, yeah, that one looks good.
Wow. Okay, that would have been pretty bad.
And I think, as I recall, we got the image around Halloween. So he sent it with the caption of like "Happy Halloween," and the whole thing was like, shaded red or orange or something to make it look even scarier than it actually was. So yeah, at that point we knew, okay, we're not going to land there. Let's go somewhere else.
Wow. So I mean, there's rovers all over the place, right? You said we've been landing on Mars since the late 70s, since 76, I think you said was the Viking, right? So there's a lot of interesting things about Mars. So, I mean, main question, right? So if you're looking at Mars and you want to know, okay, what is this planet? Why is this so interesting? Uh-huh. Main question, why is it that red or burnt orangey color? Like, what is the official color of Mars?
Right. Well, red, I mean, that's
red?
one of Mars's nicknames is the red planet.
Right,
I mean, that's when I'm writing stuff about Mars, I will frequently call it the red planet just to avoid repeating Mars or Martian over and over.
Yes.
So Mars gets its red color really from, essentially rust. So you have, and some parts though, or many places on Mars, it's interesting that it's really only skin deep, that you can uncover, or if we go and either brush off or just blow away some of the dust, you get to underneath it looks a lot darker. But we have this bright dust deposits kind of all over on Mars because Mars can have these global dust storms. So you get this stuff distributed everywhere.
Wow.
And the red color really comes from the oxidized iron, which, again, rust or hematite, the specific mineral, or other things like that give Mars its red color. So you had oxygen in the atmosphere, which is reacting with minerals on the surface to produce this iron oxide, which gives Mars its red color.
Huh. Is it sharp, the dirt, or what do you call it, dirt, or do you call it regolith?
Soil, or we're moving towards calling it soil on Mars, even though some terrestrial people say soils have to have living things in it, but we like regolith on the what we're calling soil on Mars is different from regolith on the moon
bodies.
Or other airless bodies.
Yeah. Okay. Nice. But there's oxygen in the atmosphere. Not a lot, though, right? Like you can't step out on Mars. If you were to land on Mars and step out of your capsule and breathe the fresh air, right? There's not a lot.
Correct. So Mars's atmosphere is 95% carbon dioxide, 2% nitrogen, and 2% argon. So that only adds up to 99%. So then there's other little bits, and oxygen is one of the other little bits, but it's much, much less than 1% oxygen.
But it's enough to rust make the
and that's the idea of that's where at some point in the past Mars's atmosphere probably had more oxygen,
right?
And that oxygen reacted with what's on the surface.
Okay, so compared to Earth, our Earth is mostly like nitrogen, right? 70% nitrogen, and then
80%, roughly 80% nitrogen, 20% oxygen. Is kind of the.
Okay, so only 20%. That's awesome.
But so the other thing though is not enough oxygen to breathe, but it's also less than 1% of the atmospheric pressure of the Earth. So really low pressure, no oxygen. There's a lot of different ways that you could meet a quick end on Mars if you just decided to step outside without any kind of protection.
Which goes to our earlier point, as if you were to go there, you would probably need a habitat, and you would need rovers, and you need all kinds of spacesuits to walk around. You need all kinds of things to survive on Mars. But I mean, Mars is not just it's not just a blanket of the soil, of this red soil. It's got hills and mountains. It's got one of the biggest,
the biggest volcano
in the solar system, right? So I mean, there was a past of geological activity, right?
Yes, absolutely. So when we look at the history of Mars, we see a lot of evidence early on, like I was saying earlier, that Mars was warmer and wetter than it is today. Now, it's still an open debate about how warm it is and how wet it was, but we know that it's warmer and wetter because we see evidence for rivers and lakes. So there was likely, at the very least, snow, possibly rain. These aren't like little streams, large channels, huge lakes. It's possible that there was a massive ocean. So we know that Mars was warmer and wetter in the past, and then kind of after that, Mars dries out, and then you have all this abundant evidence of what you're talking about, the volcanic activity, really, all over the place on the surface of the planet. That has really kind of resurfaced a lot of Mars. We still see a lot of craters, but there's volcanic activity all over the place. And like you said, so we have Olympus Mons that's like 20 kilometers high, the biggest volcano in the solar system.
Super big.
So MSL, or the Curiosity rover, landed at the bottom of Gale Crater, which is a 150 kilometer wide crater that's 5 kilometers deep, and right in the middle of the crater is a 5 kilometer high mountain. So it is a mountain. It's not a hill.
Yeah.
It is huge. I mean, this is, it's like rivals Mount Rainier or Mount Shasta or something. Like, it is big.
Yeah.
It's really big. It would be one of the largest mountains in kind of the lower 48 United States.
Wow.
And we're still kind of trying to figure out exactly how it was formed. One of the interesting things about it is that it was not formed so most mountains on the Earth are formed through plate tectonics, right? The continental plates kind of crashing against each other, or a subduction of an oceanic plate pushing up mountains, and that's how we get mountains on the Earth. On Mars, we don't really have plate tectonics, so you can form mountains either from volcanoes. There might be some tectonic activity, but what we're seeing in Mount Sharp is likely the result of actually the crater to some degree filling up with sediment, so dirt, rock, whatever,
Huh.
around a pre-existing central peak in the crater that we still see some evidence for, but what the mountain that we see is much, much larger than the central peak would have been, and then eroding away into the shape that we see today. So completely different form of, or completely different formation mechanism for a mountain. I can't think of any example or any place on the earth where you would ever see anything like this.
Wow.
But still, we formed this 5-kilometer high mountain, and the cool thing about it, though, is because it is this composed of sedimentary layers that were laid down over hundreds of millions of years, as we drive up the mountain, we're seeing different layers, and we get a window into Mars's geologic past. So we can learn something about, what was Mars's environment like 3.5 billion years ago. And the reason that we picked this location is that the lower part of the mountain was created when Mars was warmer and wetter, and the upper part was created when Mars was colder and drier. So we're going to have the opportunity to drive across these materials that span, again, hundreds of millions of years of geologic time,
You kinda like
where
driving
Mars
through
went
time,
under
yeah.
this, where Mars underwent this fundamental geologic change or climate change. So trying to figure out, what happened.
It's kind of like, so, I mean, I'm from Pennsylvania, so I remember driving down the highway and seeing, they blew up some of the rocks, and then you could see the layers of the
road
rocks.
cuts are the geologist's best friend.
Yeah. So it's kind of like, I mean, the mountain itself, are those, layers of rock as you drive up. I guess that would be kind of a good comparison?
Yeah, it's just on Mars, it might actually be a little bit easier to interpret some of it, because on the Earth, again, the mountain, you had the layers, kind of laid down, creating the rock, and then you'll have these other tectonic events that push them up. And in the process, things get all kinds of jumbled. But on Mars, there was no tectonism. So they the rocks got laid down, and then they get eroded away, but there's nothing that, it was pushed up from kilometers deeper or overturned, creating all kinds of confusion. So if we can get there to the right places, unfortunately on Mars there's no road cuts, so we have to do we have to use what we're given. But it's very similar to what you'd see in a lot of places on the Earth.
Wow. Okay, so another main difference, right, is I guess the atmosphere. We just had a recent discovery about how Mars's atmosphere has changed over time, right? And how what's the radiation environment like on the surface?
So, the atmosphere, so that's two things. The atmosphere, again, we know that it was warmer and wetter in the past, so that we know that the atmosphere had to be a lot thicker than it is today to hold in that heat. And we're still unclear how Mars was able to be as warm and wet as it was. There's some kind of magic combination of pressure and chemical elements in the atmosphere that had to have existed to allow Mars to be warmer and wetter, and that's still something that people are debating today. So how that relates to radiation is that on the Earth, there's a few things that protect us from the radiation environment in space. One is Earth has a magnetic field. That does a lot of the work. The other thing is we have a relatively thick atmosphere, so anything that makes it through the magnetic field is generally going to get stopped in the atmosphere. So Mars doesn't have either of those things. And there's other types of radiation as well, so like ultraviolet radiation, which is not great for people. Earth has an ozone layer. Mars, depending on the season, will have a tiny bit of ozone in the atmosphere, but not really enough to effectively shield you from UV. So you get ultraviolet light down to the surface of Mars, which on the Earth would be sterilizing. Like if you stick that's one of the things that we do on Earth to sterilize water or whatever. If you shine it with UV light that Mars is getting bathed in all the time. So the very surface of Mars is not terribly hospitable to life. But the good news is, the iron oxides, for example, are a very good sunscreen. So if you're under a couple of microns, so like a human hair's width of iron oxide, will do a pretty good job protecting you from ultraviolet light. So that's one type of radiation. The other type is, again, the kind of the space radiation environment where you have these high energy galactic cosmic rays and stuff the sun's shooting at you all the time.
Oh yeah.
So this is something that you have to be For robots, it's something that we have to be aware of as well, because we actually have to use special electronics that are like radiation hardened. For people, you have a couple things you need to do. One is you have to have some kind of shielding, and then the other is just kind of what your mission architecture is. You want to spend as little time in space as possible.
Right.
But I mean, what I think, there's a few things that you can do to shield you from radiation. Like recently, we have a radiation detector on Curiosity on Mars. Relatively recently, we were right up next to a hill doing some science, and the counts on the radiation detector went way down, because this radiation, it's not just coming from the sun, it's coming from everywhere in the sky, basically uniformly. So if you can block out any part of the sky, you're going to lower your radiation dosage. So if you're an astronaut, you'd probably want to build your habitat up close to a little hill or a mountain, and maybe one of the first things that you do when you get there, or you had robots do this before you got there, is start filling up sandbags and put it on the roof of your habitat, because you just need more mass. That's what the atmosphere is on Earth. It's just more mass in between the radiation environment and the ground. So you just need more mass on top of you to shield you from this radiation. And then again, like the UV stuff, an astronaut in a spacesuit will be just fine.
I'm imagining, like in Star Wars, like Luke Skywalker's house, how it just had the big
little
dome
on Tatooine.
made of on Tatooine, made of it looked like sand, so just like making like a sand dome.
Yeah, so you need something like that, because again, like when we went to the moon, the lunar lander was, I forget, but as I recall, like paper thin, right? Like it wasn't a long duration, or they weren't planning on staying there for a long time. So on Mars, if you're going to stay there for like a year and a half, which is generally the mission architecture says about 6 months trip to Mars to get to Mars, a year and a half on the surface, 6 months back. So if you're going to spend a year and a half on the surface of Mars, you need to do something to shield yourself from radiation once you get there.
Definitely. So in the movie The Martian, there was a severe dust storm.
Yes.
From what I understand, that's wouldn't really happen, right?
Correct.
Yeah.
So, and this is, so I got to say though, because not a knock against Andy Weir at all, because when he was at JSC a couple of years ago, he gave a presentation and said, okay, before you guys ask any questions, I know that the dust storm wasn't realistic.
He was probably very nervous about his audience. He's like, these are the guys that know. Oh, no.
So he just said, I wanted to write a book about kind of like Robinson Crusoe on Mars, and I had to do something to get him stranded there.
Right.
So the dust storm is not realistic because Mars's atmospheric pressure, again, is less than 1% of the Earth, Earth's atmospheric pressure. So even when you have very fast winds, they're not very strong. So you could have like 100-mile-an-hour gust, and it'll feel like a less than 10-mile-an-hour wind on the surface of the Earth. So it's just not strong enough to push anything over that size. The other difference is there are dust storms on Mars, and they can be planet encircling.
Right. You
which
mentioned
is
that before.
which is really interesting. Something that obviously doesn't happen on the Earth.
Right.
Thankfully.
Yeah.
But the way that it works, and you can go look at, there's pictures of this, because the Opportunity rover has been there during, I don't think it was a planet encircling one, but at least a very regional, like large scale dust storm. And the way that it looks is at the beginning of the dust storm, you have, or before the dust storm starts, you have pretty clear skies. And then something like 20 to 30 days later, you can't even see the sun at all anymore. It just maybe gets slightly lighter or brighter during the day. But it's a very gradual increase from day to day. It's not like in The Martian, here's this massive dust storm barreling down on us. Let's all go inside.
It's tipping the MAV. Yeah. It's like,
So Mars does have these really large dust storms, but they're just not strong enough to really have to worry about much.
Does it have its own weather too? It has like lightning and stuff, right?
I don't know about lightning. It might. I do know of people who have said that it probably does have lightning, and the lightning could create interesting chemicals that we see in the atmosphere and on the surface, and so maybe that's a signature of lightning. I don't know that we've ever directly observed lightning. But Mars absolutely has weather. It is still a very dynamic place. The main agent of change on Mars is wind. It just happens at a slower pace than on the Earth. But Mars has sand dunes that march across the surface. It has this dust that can blow all over the place. Mars has dust devils, so if you live in a little bit drier, more arid environment, and you see you know what a dust devil is, we see dust devils on Mars all the time. Yeah, they look kind of like little tornadoes. Yeah. Good. Yeah, a sand tornado is a good description. And we've actually been lucky with some of those. So Spirit and Opportunity. I know this happened with Opportunity. I'm pretty sure it happened with both of them. So they're solar-powered rovers. So they saw the output from their solar panels was decreasing over time because you're constantly getting dust settling out of the atmosphere. And then, so I can't remember the exact numbers, but it had gotten down to like half of the solar panel output from when it landed. And then they look at the data, and from one day to the next, it jumps back up to the same amount of power they were getting on like day one of landing. And so they look at their solar panels, and they've been completely cleaned. So what they think happened is a dust devil passed directly over the rover and did us a huge favor by cleaning off the solar panels. Like, there's no way that Opportunity would still be alive had that not happened multiple times.
Wow. Okay, so they're pretty frequent then. If they're,
this happens all the time. And
wow.
You can actually see the dust devil tracks from space. A friend of mine, Dave Choi, did some work on this where you can see dust devil tracks all over the place because what I said earlier, you have this bright red dust that gets kind of laid down uniformly over the surface. Mm-hmm. And when a dust devil comes through, it'll suck that up off the surface and move it somewhere else. So you see these tracks of dust devils all over the place. And at first we didn't really know what we were looking at. And then somebody, I forget who, said, hey, those are dust devil tracks. And yeah, they are all over the place on Mars. We have seen them everywhere we've been looking, we have seen them.
It's just amazing that you can think of, you can imagine what's going on at the surface level of another planet, as if it's just like another place on Earth, but we're talking about
and a completely different planet.
Yeah, a completely different planet. Yeah. So that is wild.
Yeah. And another thing that Phoenix saw is we actually saw snow and frost deposition. I mean, it was, teeny tiny bit of snow.
Right.
But it was snow.
Yeah, so it's kind of like how, like I said, I'm from Pennsylvania, and we get snow all the time. But here, when there's snow, everyone loses their minds.
Yes, yeah, it might be. Well, so it might snow on Mars more frequently than in Houston, but it doesn't snow a lot.
I would like to see snow on Mars. That would be pretty cool. So, being a planetary scientist and you've alluded to a lot, if talking boots on the ground, this is what you have to do, this is what you have to think. Uh-huh. I'm assuming you've thought a lot about, what a human mission to Mars would have to look like to be successful.
From a scientific perspective?
Yes.
So I would say probably the holy grail from a scientific perspective, and this is one of the things that humans would really enable, would be the ability to drill. Because we say on MSL we have a drill, and that's true, but we can drill down all of 6 centimeters. So a couple, like 3 inches, 2.5 inches. So not very far. We are literally just scratching the surface of Mars.
Yeah.
And if you want to go to a place, again, getting back to the radiation environment, the radiation, you have a lot of radiation or energy deposition in the top meter of Martian soil. Mm-hmm. So any life that existed there that was maybe, billions of years old has been either heavily transformed or completely destroyed. So it would be really hard to find the signature of life anywhere within the top meter. So we need to go deeper, and if you want to go really deep, you need humans, because drilling is something that is very difficult to do kind of in an automated way, even on the Earth. Mm-hmm. You need people there to kind of troubleshoot when things go wrong and fix stuff that breaks or whatever. So that, to me, is one of the things that humans would do. The other thing is, I think we've been studying Mars from the surface, like I said, for 40 years now, but still we've only landed in, so we have Viking Lander 1 and 2, Pathfinder, MER, Phoenix, MSL, so 7 successful landings on the surface of Mars. So that's like saying pick 7 places on Earth spread out by 1,000 miles or so each, and tell me about the entire planet. And obviously that's not like the whole history of the planet over 4.5 billion years. And by the way, you can only go about 10 kilometers from wherever you land. So we have there are so many other places on Mars that we know nothing about, that you look from orbit and say, what the heck happened there?
Yeah.
What is this? What's going on there? And there's a lot of places from orbit as well where some places we can kind of tell something about the mineralogy. Other places they're completely covered in dust, so we really have no idea what the mineralogy is of what's underneath it. So another thing that humans will give you is the ability to go farther from wherever you're starting. And again, the boots on the ground, people saying, hey, this looks really interesting, let's chase this down and go over there. Also, we would be greatly benefited by bringing samples back from Mars on purpose, where we know where they come from. Like,
right.
We have Martian meteorites, but we don't really know where they came from. So knowing the context of the samples and being able to use the instruments that we have on Earth, which are much better than the instruments that we send to Mars because of size, volume, power, whatever. We could do a lot with the sample returned from Mars, and astronauts, like from the moon, astronauts brought back hundreds of kilograms of sample. Now it's a bit more expensive to get back stuff back from Mars, so we might not have quite as many samples, but we would definitely bring back samples with the astronauts. So that's another thing that having people there on the ground enable you to do.
Yeah, knowing the science, this will be the last question, and then we'll kind of wrap up. But
okay.
Knowing the science of the planet, kind of, what are some of the key things that we have to be paying attention for to make sure that humans can survive and operate in the most efficient way? Because like you mentioned radiation a couple times. Radiation is obviously a concern, but what do we have to think about in terms of the way we move and how far we can go? And you obviously said, you already talked about a mission profile, how long we can be there.
Right. So radiation is one of the big ones. We're still not totally sure how the human body works for a long period of time in a lower gravity situation. Like, we have people in 0G, right?
Right.
But Mars is 40% the gravity of the Earth. We don't really know what the effects are of the human body. Unfortunately, that's incredibly difficult to simulate, so we probably really won't know until we go.
Right.
Otherwise, though, there are other kind of environmental hazards that you need to be aware of, like you referred to the dust. So that's something that you just need to make sure that you have good filtration systems.
Okay.
It's one of the main problems for the dust, though, is for the suits. Like, if you have a spacesuit with seals and you have joints that move, and you have dust getting into those joints, which we know it did on the moon, then that can be problematic. So, how do you design your seals? How many replacement seals do you need, or design your spacesuit to be repairable by the astronauts on Mars? But this is also kind of an open question, is that we don't really know the nature of Martian dust. We don't know if it will be kind of as sharp and damaging as some of the lunar dust, because the lunar dust and Mars dust form in two different ways. Like, we know the average particle size of the Martian dust that gets into the atmosphere is like 5 microns. So that's great. It's good to know that, but you need to know a little bit more about the size, shape, hardness, those kinds of things of the dust, about the dust when you're talking to people about seals for spacesuits and spacecraft. The other thing is being aware of potential toxic things on the surface, like perchlorate, for example, which is an oxidized chlorine molecule that the Phoenix lander discovered in 2008. And so we know that perchlorate is toxic to people, but at really high quantities. So it's less of a concern for inhalation for people, however much perchlorate might be in the dust. So as I like to tell people, as long as your astronauts are not eating kilograms of soil every day, they're fine. But
kilograms
it really would have to be
soil.
Yeah, right. So that's generally fairly low on hey guys, don't eat dirt. Yeah, okay, we got it. We checked that one off.
It's very tempting, but
but so the one thing that we do have to do more research into is if you grow plants in soil that have perchlorate, there are some plants that can concentrate perchlorate in certain parts of the plant. So you need to know, like, okay, if we're planning on living off of this, first of all, can it grow in a soil that has perchlorate? And if it does, where does the perchlorate go? Is this something that we need to be concerned about? So those are kind of questions that we're answering. But the exciting thing is that we have the data to actually be able to address those questions, right?
Yeah.
Like, I mean, 40 years ago, at the end of Apollo, when we first talked about going on to Mars, we didn't know any of this stuff.
Right.
We hardly knew anything about Mars, but now we have a significant amount of experience and a large body of knowledge about what the surface of Mars is like, what all the stuff we talked about today, what is the weather like, what's the temperature, what's the pressure, what's the chemical composition, what's the mineralogy, what are the physical properties of the soil, if you want to build something there or land something, what's it like, what are the things that we need to worry about. And that's what's really kind of amazing about the journey to Mars right now, is that really for the first time we have the information to go out and we know the questions that we need to answer. We don't know the answers to all the questions yet, but for the most part, we know a lot of the questions that we need to answer. Mm-hmm. And I'll just add one final thing, so you don't think it's all bad. There's a lot of stuff, and a lot of the work that we're doing isn't just what are the bad things about Mars, but what's on Mars that we can use for humans to help enable future exploration.
Yeah.
Like there's an instrument called MOXIE, and sorry, that's an acronym that I don't know what it stands for, but basically it ingests atmosphere and it breaks the carbon dioxide and oxygen, so you're forming oxygen, which the idea is you'd use that for your oxidizer in rocket fuel.
Nice.
And you can also, one of the things that I'm directly involved in is trying to extract water out of Martian materials. So water can be really useful because astronauts need water to drink, for food. You can break the water through electrolysis or other ways into hydrogen and oxygen. You can breathe the oxygen. Hydrogen and oxygen can be used as rocket fuels or fuel for a fuel cell. There's all kinds of stuff that you can do just with water. And so every kilogram of material that we don't have to bring with us makes it more likely that we will actually be able to go, because it lowers the cost and complexity of the overall mission. So we're trying to figure out from what is on Mars today that we can use to our advantage. And again, these are questions that we're now being able to answer based on the exploration work that we've done over the past 40 years.
I'm excited. I want to go to Mars right now.
Me too. Let's do it.
That was a nice little summary of all the things we talked about too. That was great. Well, I think that's all the time we have. Doug, thanks for coming on the show today.
My pleasure.
That was awesome. So cool. I learned so much about Mars. I had so many questions, and almost all of them got answered. For the listeners, if you do want to know more, I'd be surprised, but actually there are way more questions. We can talk forever about Mars. But if you want to stay tuned after the music that we have at the end here, we'll talk to all the sites you can go to and learn more, and maybe you'll find a question that you want to ask, and we'll tell you how to submit that. So thanks again, Doug, for coming on the show. We'll
You're
see
welcome.
you maybe next time, maybe one more time. Who
Sure.
knows?
Stop of the space shuttle.
Roger, 0J, and I feel
Shuttle has cleared the tower.
a feast for all mankind.
Actually, a huge honor to break a record like this.
Not because they are easy, but because they are hard.
Never keep still. Welcome to space.
Hey, thanks for sticking around. So today we talked about Mars, the red planet, and everything about it. But when I say everything, I don't truly mean everything. Obviously, there's a lot more. We may do another podcast in the future, but if you want to know more about the red planet right now, just go to nasa.gov. Right at the top, there's a little gray bar, and you can see the Journey to Mars. That's one of our campaigns, and if you click on that tab, you can learn all of the new things, all of the new features and all the new articles, scientific findings, right on that page. So just click on the Journey to Mars page to go there. On social media, we're pretty active. Doug Archer here, Dr. Doug Archer, is part of the Astromaterials group, what we call Aries. You can find them on Facebook and Twitter and Instagram. And you can also go to the NASA Johnson pages, Facebook, NASA Johnson Space Center. We're also on Twitter and Instagram. On any of those pages, just use the hashtag AskNASA on your favorite platform, whichever one you like, and submit an idea for the show. Maybe you have a question about Mars, or maybe you have a new idea or a new question that maybe we can make a whole podcast episode out of. So make sure to mention it's for Houston. We have a podcast, and we know to bring it on this particular show. This podcast was recorded on April 20th, 2017. Thanks to John Stoll and Alex Perryman for producing the episode. And thanks again to Dr. Doug Archer for coming on the show. See you in 6.79 sols. That's a week in Mars. You know what? Never mind. We'll just see you next week. Houston, we have a podcast. Welcome to the official podcast of the NASA Johnson Space Center, episode 142, Preparing for Mars. I'm Gary Jordan. I'll be your host today. On this podcast, we bring in the experts, scientists, engineers, astronauts, all to let you know what's going on in the world of human spaceflight. We have nearly 20 years of continuous human presence on the International Space Station. That's nearly 20 years of studying the human body, understanding systems, and fine-tuning operations for how to conduct human spaceflight missions. And not to mention the decades of human spaceflight missions and experience before that. A lot has changed over time based on what we've learned, and a lot of questions have come up that are important to understanding how things will change when traveling to Mars. You might think, that's a lot of experience already, so why don't we just go to Mars? It's hard to imagine just how hard Mars is. It requires near absolute perfection, and any deviation may be a risk to the safety of the humans on board or the success of the mission. So the question is, are we ready? You could even ask, how ready are we? Luckily, we have an organization right here at the NASA Johnson Space Center and all across the agency looking at what we have and what we need to make a Mars mission successful. Michelle Rucker is a Mars integration lead at Johnson Space Center for the Mars Integration Group, a team that spans across all of NASA. She's a 33-year veteran of NASA, joining in the aftermath of the Space Shuttle Challenger accident and supporting the investigation by conducting booster material tests and analysis. She has participated in a range of exciting projects, such as the International Space Station Environmental Control and Life Support Systems, hypervelocity impact research, spacesuit and spacewalking tools, space station exercise equipment, system engineering, and Orion crew exploration vehicle testing and verification. She currently leads the Mars Integration Group, developing crewed Mars mission concepts. She holds 2 U.S. patents and has authored numerous technical publications. So on today's podcast, Michelle goes over the details of what we know, what we have, what we need, and how NASA's Artemis program that will establish sustainable human presence on the moon will help inform and fine-tune the ideal mission structure for a Mars mission. And I hope you like this topic because there's going to be a lot more. This month kicks off monthly episodes that are all about a Mars mission, and we'll call it Mars Monthly. Over the next few months, or maybe even the next year, we'll dive deep into the various elements we discussed today with Michelle. So, here we go. Preparing for a human mission to Mars with Michelle Rucker. Enjoy.
T-minus 5 seconds and counting. Mark. Launch commit lights are correct.
There she goes. Houston, we have a podcast.
Michelle Rucker, thanks so much for coming on the podcast today.
Thanks for having me.
So this is an interesting topic. I'm really excited to talk about how we're preparing for Mars. There's a lot to consider, and it seems like it's a pretty small group doing it. I want to get a little bit of sense of your background, though, to understand what has to go into the people that are actively thinking about what we need for Mars. What's your background?
So I was born in Alaska, so extreme environments don't scare me. So that's probably the first requirement for thinking about Mars. I went to school here in Houston at Rice University. I've got a couple engineering degrees in mechanical engineering. I started my career at the White Sands Test Facility in New Mexico.
Oh, right at NASA. Okay.
With NASA, yeah. If you're not familiar with White Sands, we do all the fun hazardous testing stuff out there. So that means blowing stuff up and setting it on fire and shooting micrometeorites at it. So I spent the first part of my career trying to destroy spacecraft. But at some point, you get tired of that and you want to start creating. So I transferred here to Johnson, worked on the space station with the life support systems. I did stints with the exercise equipment. That was one of the funnest jobs I did.
Oh.
I also worked the Constellation program for both the Altair project and the Orion project. And then when the Constellation program wound down, I started doing exploration for the first time. So I'm relatively new compared to some of the folks who've been working on Mars for years now. I've only been doing Mars work for maybe the last 8 or 9 years.
That's still significant, but I think what's important is you have that breadth of experience. You did a little bit of this, a little bit of that. Space station's really important. We're going to fold that into today's story a little bit. So I think that's a really good background to have. Now you say you're new, but 8 or 9 experiences. That's 8 or 9 years. That's a lot of experience to me. So just from what you've learned in your 8 or 9 years, thinking even just all the way back actually to when we first started here at NASA thinking about Mars missions and what we need for Mars missions, what were we thinking about?
So Mars missions are the history within NASA is sort of interesting. Only a few weeks after the Apollo 11 landing, Wernher von Braun put together a proposal for a Mars mission, essentially taking the lunar hardware that he just developed successfully for the Moon and supersizing it and going to Mars. So that was an initial proposal. At the time, the agency was focused on the Moon. When the Apollo program wound down, NASA focused a little bit more on low Earth orbit. So the shuttle and the station era, we were a little bit closer to home. But even during that period, there was a small office, both here at Johnston Space Center and across the agency. There were small groups working on some of the Mars technologies, thinking about some of the mission concepts. To me, Mars is a system engineering problem as much as anything. We know how to do most of the individual pieces. It's how do you put it all together into a single mission concept to be successful.
I see, and that's where some of the work you're doing is coming in. It's taking all those separate pieces and thinking about them and actively putting them into what we're thinking about now, what resources and technologies we have now, but thinking of just further ahead and way further out.
Yes. So taking the technologies we have, looking at whether we need to supplement those with new technologies. Do we need to extend the technologies a little bit more? Thinking about operations. Operations have changed a lot over the years. Now we've got the commercial players involved, and that's an exciting new development. So things have become a little bit more streamlined. Some of the things, the way we did business, even for procurements, back in the shuttle and station days, we're developing new and faster techniques for doing procurement. So that's exciting as well.
Okay, so let's go right into it. Thinking about those challenges for Mars, the things that are going through your brain all the time. What are we thinking about when it comes to what to do, what to integrate into a Mars mission?
So what's interesting about human spaceflight is the entirety of human spaceflight has literally revolved around the Earth. Everything that we did with the Moon revolves around the Earth. Everything we did with the space station, with shuttle, it was all revolving around the Earth. In order to get to Mars, we have to change our coordinate frame of reference. We have to start thinking about revolving around the sun. So first we have to chase Mars around the sun to catch it. And then once we get there, Earth wasn't where we left it, so we've got to chase Earth back around the sun to get home again. So it's a bigger scope problem than the types of missions that we've been focused on. So the challenges I like to break into really sort of 3 pieces. There's the getting there, the living there, and the coming home. So you ready to step through the pieces? All right. So the getting there. So the trajectory guys like to say that it's 2,000 times farther, and that's like the odometer reading, to get to Mars and back versus trying to get to the Moon and back. And that, again, that's because both Earth and Mars are moving, so it's not just a straight line there, a straight line back. You've got to chase these planets around the sun. So 2,000 times farther than the Moon. It only took us a few days to get to the Moon. You can go to the Moon and back in a week. To get to Mars and back, that's a little bit different. How long it takes, the transit time, is a function of when you go, where the planets are relative to each other at the time that you leave, and what kind of ride you're riding in. But typically, we're talking 2 to 3 year mission durations. So that's a much longer mission duration than the types, even the longest expeditions we've done on space station to date. It's only been a year. So these are very long missions that we're looking at. So long duration mission means you need a lot of stuff. You need a lot of food, you need a lot of oxygen, you need a lot of spare parts, a lot of consumable parts. And that means we need to launch a lot of stuff from Earth, or we need to figure out a way to either make it or find it somewhere, either at our destination or on the way. Once we get to Mars orbit, we'll need to land a fairly large payload. To date, the largest thing we've landed on Mars is the Curiosity rover. That's about 1 metric ton. The smallest human-rated vehicles we've been able to squeeze, we're looking at crews of maybe 4 people. A crew of 4 is still probably going to require about a 20 metric ton lander. So that's 20 times as big as anything we've landed previously. And unlike Earth, Mars doesn't have a nice thick atmosphere where we can use it to help slow down. So our entry, descent, and landing is challenging. The other problem with Mars is global dust storms. You may have read about the Opportunity rover. Unfortunately, met with a tragic end with the dust storm in 2018, I believe. So dust storms can obscure the landing site. So that's another thing. We need technologies that would be able to deal with that. Or we need to have good weather prediction and be able to plan around dust storms. So once you get there and land, then there's the living there. So in some ways, Mars is a lot like home. There's a day-night cycle on Mars. A day is a little bit longer on Mars. It's about 24 hours and 37 minutes. It's got mountains. It's got valleys. I've seen photos that the rovers have taken, and it looks just like the desert Southwest in some places. So lots of beautiful vistas.
Wow.
It has seasons. So a Martian year is about twice as long as an Earth year, but it does have seasons. On a balmy summer day, it can be as warm as 80 degrees. So in some ways, Mars is attractive because it seems hospitable. It's also exotic. It's got 2 moons, Phobos and Deimos. If you're into Greek mythology, they were the twin sons of Ares, I believe. They're itty-bitty moons, but I've always thought it was kind of cool that if you were sitting on the Martian surface looking up at the night sky, the moons cross each other in orbit, which is kind of cool.
Wow, that would be a sight.
That would be pretty neat, yeah. But Mars is also challenging. So it's got reduced gravity. Humans are used to 1G. And Mars is reduced. If you weighed 100 pounds on Earth, you'd only weigh about 38 pounds on Mars. But because there is gravity, the challenge is that carrying around a big, heavy spacesuit becomes more problematic. We never worried about that too much in the ISS days because with microgravity, a big, bulky spacesuit wasn't really a problem. But on ISS, you don't really walk. You use your hands to translate around. So our spacesuits will need to be redesigned for a planetary surface. Once you get on the surface, the humans are going to need a lot of power. Got to upload those selfies, right? Got life support, communication, mobility, whatever science we're going to do on the surface. So we'll probably need a lot of power. The conventional wisdom is, well, we're in space. We just use solar. But Mars is a little bit further from the sun than Earth is, so there's a reduced solar energy there. The other problem is the dust storms. The dust storm, that's what happened with the Opportunity. Mm-hmm. The dust storm knocked out the solar energy, and poor Opportunity didn't make it. So we need to look at some alternative sources for power. And it can get cold in some places in some seasons. So it's a pretty extreme environment. So now if we finished up our mission on Mars, we're ready to come home, all of the Mars missions to date, all of our robotic missions have been one-way affairs. We've never actually tried to launch anything from Mars. So Mars does have a lower gravity, so getting something off the surface of Mars would be easier than getting something off the surface of Earth. But we still estimate about 7 kilograms of propellant for every 1 kilogram of mass we're trying to get into orbit. Each crew member is going to be, maybe 100 kilograms. So you're talking about a lot of propellant. We've estimated up to 38 metric tons for 4 crew with science equipment and their EVA suits and so on. So that begs the question of, do we bring all that propellant from Earth and then try to land it? Or do we figure out a way to make propellant there? Those are some interesting questions. Once you get back into space, get in your deep space transport, come back to Earth, you've got the Earth reentry problem. It's about 11 kilometers per second reentry back into Earth. That's what Orion. That's the challenge Orion was designed to overcome. So those are the challenges.
Yeah.
And all of those taken together could be daunting if you were trying to start from scratch to solve all those challenges. But the cool thing about what NASA's been doing ever since von Braun first proposed Mars is we've been whittling away at these challenges piece by piece, so we don't have to start from scratch. A lot of the projects that you may have heard about recently, Artemis, the human landing system, the Gateway, plus ISS shuttle experience, some of the EVA suit development work that's been going on, all of that will contribute to helping us solve some of these challenges.
That's significant. That's a lot of consideration. I mean, that was what you just described right there. That little packet was the Mars mission. It was getting there, it was living there, it was coming back. It was in those three sections. And I'm smiling over here. You can't see it because we're on the podcast. I'm smiling, but I mean, you make it sound like, and that's it, and that's what we need to do. But I know it's so hard. There's a lot of challenges that are associated with this. In terms of what we're investigating, let's kind of dive a little bit deeper into some of these challenges, starting with getting there. I pulled out a couple key elements. As you were going there, you're like, oh, that's a challenge. But I know it's a really big challenge. So one of them was just distance. Just being far away makes everything so much more complicated. Because with being far away comes, you have communication delays. You're talking about a significant amount of energy to get there, a significant amount of time to get there. And then the positions, like you did mention this, the positions of Mars and Earth have to be in such a way that meet the requirements to actually go catch up with Mars. That's all very significant things.
It's pretty astonishing that there are smart guys who can calculate precisely where Earth and Mars will be at any given instant in time with such phenomenal accuracy. It still amazes me. We actually rely on, we've got a team here at Johnston, the Maya team, that does a lot of trajectory analysis. We also use some folks at Langley Research Center that do trajectory analysis. And also we've got some team members at the Glenn Research Center that help us with that. So yeah, we spend a lot of time trying to figure out exactly who's where when. It's on ISS, if you run out of something, it's pretty easy to resupply it. If you're halfway to Mars, it's a little bit harder. You can't really get supply on demand, so you have to do a lot of logistics analysis, predict exactly what you'll need when you'll need it. One of the cool projects we're working on right now with ISS, we're talking to them about using ISS to help refine some of our logistics models. They do really good tracking of what goes up and down, but because they have on demand, they don't have to necessarily predict very far in advance. We'll have to predict out up to 2 or 3 years in advance. So one of the things we're doing is talking to them about let's start developing some models to predict what you'll need on ISS, and then we'll look at actuals and see how close we came to that. So we're using ISS today as a way to help refine some of the tools that we'll need for Mars later.
Interesting. You're almost, it's kind of like over planning, like you're not just resupplying what you need on the space station, because as you mentioned, it's your time constraints aren't as drastic as Mars. So let's just pretend that we have to model what we need, what we will need, what we're going to run out of for the next 2 years. So ISS is the perfect place to practice that.
We're also using ISS we're in discussions with ISS to use returning crew members as a Mars analog. So after 6 months in microgravity on ISS, physically they'll be at about the same condition as a crew that's about to land on Mars. So we've been working with the Human Research Program to develop some experiments where returning ISS crew members would do some simple tasks, nothing that would be dangerous for them, but just to try to understand what the crew could be expected to do on Mars. We'd obviously try to automate as much as we can, But if the crew needed to go do an emergency EVA to go repair something, for example, the question is how soon after landing would they be able to do it? After having spent 6 months on ISS, there's an enormous crew of people here on Earth that greets the returning crew and picks them up and carries them where they need to go, and doesn't let them do anything strenuous for the first few days. They won't have that opportunity on Mars. They could potentially be asked to do things that they would never be asked to do here on Earth. So we want to understand what the capabilities will be. Are there countermeasures we can use to try to make sure that they're in good enough physical condition, strong enough, with good enough balance to be able to do not necessarily strenuous things, but things that could be dangerous if you are far away from a doctor, you lose your balance and fall, for example. And so we try to think ahead to those sorts of things and use the available programs that we have in place today, sort of piggyback on those where we can.
Interesting. So it's like you're using crew members returning to the planet as a way to think about if astronauts were on a very long journey to Mars, and you said, what was it? It's like 9-ish months to get there?
Again, it depends on which opportunity, exactly when you leave, where the planets are with respect to each other, and which propulsion system that you're using.
That's an important distinction. But regardless, it sounds like it's going to be a relatively long time about what we're doing now on the space station, give or take. So when you land, I guess, what the human is going to be able to do, what we could do to try to countermeasures we can put in place to see how we can maybe help them get ready to do something. Another thing that's coming to my mind is technology to maybe support, maybe holding them in place for a little longer, life support systems and the necessary provisions, so that maybe if during this recovery phase they just need to wait it out, maybe they have that ability. Because I know, I've been out to Kazakhstan. I've carried an astronaut, and I know they are just like, but they get put right to work, right? So they have to do these right. Tests that you're saying right now. They have to do these tests to test performance. So they're up, they're moving, but they're dizzy. They're dizzy, and they've had a long journey, and their bodies are adjusting. So modeling that is important.
That's one of the unknowns is. So here on Earth, they don't have to get up and do anything right away. There's a crew there to help them. One of the things we want to know is how soon could they safely get up and do certain tasks without risk. So that's sort of an exciting area of research that we're partnering with HRP on. Back on the transit question, how long does it take to get there? So
sure.
One of the things that we're looking at is can we minimize either how much propellant it takes to get to Mars and back, or the transit time, or both. So we're looking at a range of new technologies. Electric propulsion is an interesting one. So the Gateway will be using solar electric propulsion. Those electric thrusters are of interest. We sort of see that as the evolutionary path for the Mars system. So Gateway essentially becomes our test bed for that propulsion system. Gateway also, the other thing that Gateway does for us is it's outside Earth's protection. So it'll give us some deep space experience with in a harsher environment than a little bit closer to Earth, with the radiation and so on. Long duration missions, that was one of the challenge because of the distance to Mars and back. You're looking at long durations. ISS has already given us the long duration human exposure to spaceflight, so we have a much better understanding of that than back at the time when Wernher von Braun first proposed a Mars mission. ISS has also given us a lot of long duration equipment experience. We understand, the mean time between failure on certain types of systems. We're looking at regenerative systems, trying to be more self-sufficient. So ISS has done a lot for the Mars concepts. The new commercial partnerships that some of the launch capabilities that we have available now that von Braun didn't have if we do need to launch a lot of propellant to get to Mars, we have more options now than we used to have. So that's exciting.
Yeah.
Being able to land large payloads on Mars, we're developing and testing several different technologies. My personal favorite is the Hypersonic Inflatable Aerodynamic Decelerator. The acronym is the HIAD. That's a pretty cool system to be able to use it's a big giant inflatable that gives you enough surface area to help slow down your payload before you land on Mars. The other thing Gateway will do for us is, I always say that lunar landers coming and going from Gateway to the lunar surface will look very similar operationally to Mars landers coming and going to the deep space transport. So Gateway will offer us an opportunity. Gateway paired with the human landing system will offer us a lot of relevant operational experience that will be directly applicable to what we want to do on Mars. On the living there challenges, we already have a lot of experience with microgravity, which we need for the transit leg of the mission from our shuttle and ISS experience. But the Artemis program will give us some reduced gravity, lunar gravity experience on the surface of the moon that will have some applicability. For example, spacesuits. We'll need to develop a planetary suit for the moon, something that you can walk around in. The hip joints, the boots that we use on ISS are not really appropriate for walking around in a dusty environment. So that's something that we'll get from the Artemis program. And then surface power, we're looking at a couple options. Oversizing the solar arrays. More surface area is one way to go. Another way to go is a compact fission power system. Our technology mission directorate is looking at some alternative power sources to solar that are of interest to us. The moon is cold and dusty, just like Mars will be, so that gives us, especially during the lunar night, gets pretty cold. So Artemis will give us a lot of experience with the extreme environments. And then on the coming home again, we're looking to the human landing system, the lunar ascent element may be directly applicable. Getting from the lunar surface back up to Gateway is not unlike getting from the Mars surface back up to Mars orbit. So we're looking to that program for maybe some get ahead on a Mars ascent vehicle. And then, of course, once we get back to Earth orbit or cislunar space, Orion has already solved the problem of getting the humans back to the ground again. So that we check that off of our to-do list. We just rely on Orion, and so a lot of the challenges have been whittled away, or have been at least whittled back enough that they're within reach now for us to use for Mars.
Yeah, I pulled out a couple of them because you went through those same three key areas: getting there and living there, and then coming back. I was thinking about things that we either have or are working on right now. Regenerative life support was one that I pulled out because I know that's an important part of living and working on the space station, which we've been doing for almost 20 years now. And developing those technologies, that's just something with and is going to be needed for Mars missions, something that we have. But the one thing I was really looking forward to is all this Artemis stuff that you're talking about. You're talking about all these technologies that are helping us get to the moon, yes, but in a sense, there's a lot of applications and important applications for a Mars mission. That was one thing I think it can't be really understated, because we talked about how hard Mars is, but this Artemis as almost a practice for Mars and preparation for Mars and data gathering for Mars, that's really important.
Right now, we're thinking of the moon as our test bed.
Yeah.
We will, obviously, the cheapest place to test these things is on Earth, and we will test as much as we can on Earth. I'm sure my friends at the White Sands Test Facility are excited about doing a lot of hazardous testing out there.
All right.
So we will test as much as we can on Earth. But at some point, you've got to get some relevant space experience. there's only so much you can do in microgravity. Microgravity helps us test the transit leg, but it doesn't really do much for the planetary piece of it. The moon gives us that. It gives us operational experience, a lot of materials, reliability experience. We're pretty excited about all of the testing that we can do on the moon.
Yeah. Now, the group you're in and the work that you're doing is it informing? Is it advising? Is it actively thinking and writing down requirements for what you think we'll need for a Mars mission, or what we think we should be working on now to prepare for a Mars mission?
We're not quite to the point of writing requirements.
Okay.
With one potential exception. So we've got the habitat broad area announcement, the BAA effort that's going on. That was a procurement to look at an in-space habitat, which would potentially have applicability as the deep space transport habitat. So that is one specific procurement where very high-level requirements have been defined. We're not quite to the point of defining requirements for many of the other systems yet, but we are developing concepts of operations. Being able to jump into requirements should go pretty quick when we're ready to pull that trigger.
Okay. But you're thinking about at least the elements that you'll need, and we went through a lot of them. You just mentioned a habitat. I mean, one of the main parts of a journey to Mars is the actual journey to Mars, is getting there. So there's going to be some form of a vehicle, transportation technology, whatever, to actually transit from Earth to Mars, from Mars to Earth. So thinking about what we might need to, what that may look like, what we'll need to consider, because it's a long time. It's going to be a long time. So thinking about those things ahead of time is really important. And then another part that I pulled out, besides your three, thinking about the technologies we have now in our testing, thinking about the technologies that are coming up for Artemis. Another part that I pulled out was, and this is a very important part, the human element. Thinking about what a person is going to have to deal with. And you already talked about the landing, considering a landing from the International Space Station from low Earth orbit, having that be a model for what a Mars mission would look like. It sounds like there's a lot of human components for Artemis as well.
Correct.
Yeah.
Yeah, our team, we are so lucky. Don Pettit has been assigned as our crew rep.
Wow.
And he's so awesome. If you haven't ever Googled his ISS YouTube videos,
they're fun.
He is fun to work with. So Don's been involved with us. Yes, we have been doing a lot of thinking about the human systems. A lot of the Mars focus of the last few years was with the science, with the rovers, the robotic missions, the science missions. The human missions are completely different. The science missions have taught us a lot about Mars, about the conditions on Mars, what we can expect on Mars, and that is extremely valuable to help us design for the human systems. But the Curiosity is just a few watts of power. It doesn't really need very much power. Humans are going to need kilowatts of power. So it's once you put the humans in the system and you start trying to run life support systems and just the level of safety requirements that you need to be sure. You need to have a plan B and a plan C. I always give my friends at JPL a hard time because their robots, they don't need food or water or bathrooms, and the human systems, the humans will need all of those things. So there's a whole new level of stuff that has to be thought about for the human missions that the robotic missions never really had to worry about. It drives power. Once you have more power, you need more thermal control. Once you have more thermal control and more power, that's more structural mass. So these things tend to snowball a little bit, and that's why our systems end up being much bigger than the robotic systems are. People always ask, well, why not just send robots then? Why not just send robots? Do we really need to send humans? That is a debate that will rage for the ages. What the scientists will tell you is that the humans can do in a day what it would take the robots to do a year or more to do. So yes, there's a compelling reason to send the humans. The humans can make real-time decisions. Humans can fix things that break. When poor Opportunity got caught in the dust storm and the solar arrays were covered, there was nobody there to dust them off. So unless you've thought through that and planned for that contingency with the robotics, that's the kind of thing that if a wheel gets stuck somewhere, the humans can get out and deal with that, whereas the robots can't. So I can understand both sides of the argument. I happen to work on the human spaceflight side, so I'm a little bit more predisposed to that side.
Sure. But I think maybe you might have a better appreciation than most for maybe living on Earth and what Earth has to offer, and things that maybe people don't consider when they think, why are we not on Mars right now? Let's go to Mars. You're like, no, it's really hard because there's a lot of things that we're doing right here on Earth that are just, we don't even recognize. Our conveniences are just, they're, if I was thinking, one thing I was thinking about when you were talking about a journey to Mars and the distances and bringing things with you, I just did a road trip to Florida. It took me 17 hours. And yes, I packed the car full of waters and snacks, but I stopped for coffee, for a bathroom, for, just to take a break because I could. And I could get out of my vehicle and I can kind of get more provisions and I can use other facilities and then I could get back in that vehicle and I can keep driving. But it's not a luxury for a journey to Mars. I'm sure you have a better appreciation than most for this.
So being from Alaska, I have a very good appreciation of this. So the reason I'm from Alaska is because back in the 50s, the U.S. government was trying to encourage more people to move to Alaska. They were trying to open up the economy there. And one of the challenges of getting to Alaska was it was really far away, and there weren't a lot of gas stations on the way, and nobody could really carry that much gas to get all the way to Alaska. So they offered homestead opportunities to folks who were willing to set up gas stations. And my maternal grandmother moved to Alaska, set up a gas station near Palmer, and that's why my family was in Alaska. So for me, it doesn't bother me at all to think about eventually setting up waypoints between here and Mars to refuel vehicles. I know some people are overwhelmed by the sheer difficulty of that. It's hard and it's dangerous, and it is, but it's probably no more daunting than it was to my grandmother moving to Alaska with a couple little kids in tow and setting up a gas station out in the wilderness at the time. So yeah, it's hard, but there are people here on Earth who are up for that challenge.
You definitely have a better appreciation. It's even in your family. Just working on this and thinking about Mars and all the challenges that have to be answered and thought about before we actually go there. But thinking about some of the things that are in the near future for Artemis and some of the answers that we might get, some of the questions that we might continue to come up and that we might have to learn. What are you most excited about for this near future going to the moon and thinking about some of the things that we might be able to answer for a Mars mission there?
I spent most of my career working with shuttle and space station, and those were really fun programs to work with. We were, launching humans pretty often, and we were doing lots of interesting things. Going to the moon is a whole different set of challenges. It's some of the same challenges as you still have to launch people. There's still danger and risk and the things involved with that. But landing on the moon, that's a whole different set of challenges than just going up to space station. Working on the moon, that's a whole different set of challenges. to me, that's the most exciting. It's the unknown unknowns, the things we don't know about. We learned a lot with Apollo, but those were very short missions. Being able to stay a little bit longer on the moon, which is probably what we'll need to be able to do for Mars, will just give us a lot of information. We'll learn what doesn't work, and I think that is almost as valuable as designing things that you hope work. Knowing what doesn't work is pretty important.
That's incredible. Michelle Rucker, thanks so much for coming on He's Do We Have a Podcast today.
Thank you so much.
Houston, go ahead.
Dock of the space shuttle.
Roger, 0G, and I feel
Shuttle has cleared the
Became
tower.
a theme for all mankind.
Actually, a huge honor to break a record like this. Not because they are easy, but because they are hard.
Never Houston. Welcome to space.
Hey, thanks for listening. We have some bonus content for you at the end of the show, so hang tight. First, the credits. This episode was recorded on January 8th, 2020, thanks to Alex Perryman, Pat Ryan, Nora Moran, Belinda Polito, and Jennifer Hernandez. Thanks again to Michelle Rucker for taking the time to come on the show. Hope you like this topic because there's going to be a lot more. This month kicks off monthly episodes all about a Mars mission. We'll call it Mars Monthly. And over the next few months, maybe even a year, we'll dive deep into the various elements we discussed with Michelle today. Last month, NASA released a new podcast, NASA's Curious Universe. Our universe is a wild and wonderful place, and in this podcast, you'll join NASA astronauts, scientists, and engineers on a new adventure each week. Take a listen.
Before an astronaut ever sets foot aboard the space station, they have to train somewhere you might not expect. This isn't just any old swimming pool. It's the Neutral Buoyancy Lab, located at NASA's Johnston Space Center in Houston, Texas. This special pool contains 6.2 million gallons of water, enough to fit 9 Olympic-sized pools inside. It's where astronauts like Nick come to train.
So the pool is this gigantic pool. It's 200 feet long, it's 100 feet wide, and it's 40 feet deep. It is enormous. It's still not big enough to fit the entire space station in it, but it fits full-scale, large chunks of the station so that we can practice, and that's our training ground.
The pool is where astronauts first get acquainted with the armor that protects them from space, their spacesuit. And that can be its own challenge. First thing, you've got to suit up. It can take about 45 minutes and the assistance of multiple suit technicians to get the suit on, checking to make sure that every piece is fitted and working properly, from the helmet locking into place to the gloves fitting around every finger.
You have to learn how to use the spacesuit because it's not like wearing clothes. It's constraining and it limits some of the things you can do. It's fatiguing because of the pressure of having it stiff, and so you have to learn how to use it, and that takes hours underwater getting to know your spacesuit.
Once you have the suit on and it's been double and triple checked, you can prepare to enter the Neutral Buoyancy Lab. Even though you're not out in space just yet, the pool will simulate what you might feel once you're out there. Why? Because being underwater simulates weightlessness.
The Neutral Buoyancy Lab is there to train us because that's one of the places or one of the ways that we can try to simulate being weightless. So that idea of neutral buoyancy.
It's called neutral buoyancy because when you're in water and you don't sink, but also you don't float, you're completely neutral. It's like you're hovering in place.
And so it feels as though I'm weightless and I can maneuver myself around the outside of the space station and have the experience of working in a weightless environment. And so we're constantly trying to balance out the weight of an object with its buoyancy so that things just float in front of you.
Weights and flotation devices are carefully combined to let astronauts feel what it's like to be weightless in space. When an astronaut is training in the pool, their backpack, the primary life support subsystem, is filled with air they can breathe and instruments that monitor their health.
You've got to get everything straight because once you go underwater, that's all you've got are the tools you took with you. And you're going to be down there for 6 hours.
That's about the amount of time it takes for a spacewalk in actual space. Once you're in the pool, waterproof instructions are attached to your arm, and you rehearse the spacewalk as if you were doing the real thing.
All right. Nick, before we get started on that, if we can just
Yep.
help me guide that out. Much
The whole
appreciated.
time, a team of people is watching every movement of your practice spacewalk. They monitor the pressure inside the suit and the temperature. And the test director is making sure that the whole process is going according to plan.
Good teamwork there. Exactly.
So I need to float a little bit higher on this end. Okay, so that's
Good alignment.
Trained scuba divers guide you around a replica of the outside of the International Space Station.
yeah, and I
Looks
can
good here.
yeah, we're aligned down here.
Okay.
Having this full-size mock-up of the space station underwater allows us to essentially memorize where every handrail is, where every handhold is, and if I'm going to work in a particular location on orbit, I will have seen that and understand that location on the ground.
If you like this clip, you can check out the full episode at nasa.gov/podcasts. Curious Universe is right at the top. Make sure you subscribe to get the latest. They have a new episode coming out on Monday. Thanks for sticking with us to the end. Give us a rating on whatever platform you're listening to us on, and tell us how we did. We'll be back with a new episode of Houston, We Have a Podcast next week. Houston, we have a podcast. Welcome to the official podcast of the NASA Johnson Space Center, episode 147, Concepts Near Science Fiction. I'm Gary Jordan, and I'll be your host today. On this podcast, we bring in the experts, scientists, engineers, astronauts, all to let you know what's going on in the world of human spaceflight. So back on episode 142, we chatted with Michelle Rucker about what it takes to prepare for a Mars mission. Michelle was super engaging and very thorough about the different elements to consider when thinking about how to be ready for Mars. I got really excited about the topic, and Michelle and I got to talking after the recording. We thought, what if we dedicated time to each element of a Mars mission? Rendezvous with Mars, entry, descent, and landing on Mars, eating, living, exploring. What if we dove deep into the challenges of each of these parts of a Mars mission? Well, thanks to Michelle and the Mars Integration Group here at NASA, we're going to make that happen. This year, stay tuned for more episodes that dive deep into the challenges of a Mars mission and the requirements to make that successful. So on today's podcast, we bring in Jason Derleth, Program Executive for NASA Innovative Advanced Concepts Program at NASA's headquarters in Washington. To help set the expectations for what's to come, Jason dives deep into how many of us think of a future exploration mission based on science fiction movies, TV, and books. See, in the science fiction universe, we've explored the cosmos in all kinds of ways. Jason makes some of those technologies we think about in science fiction, things like cryosleep, gigantic space stations, propulsion, and he applies it to how an actual mission to deep space might just work. So here we go. Crazy ideas of science fiction that just might work with Jason Derleth. Enjoy.
T-minus 5 seconds and counting. Mark. Launch commit light circle correct.
Here she goes. Houston, we have a podcast.
Jason, thanks so much for taking the time to talk to me today on the podcast.
Oh, it's a pleasure to be here, Gary. Thank you for interviewing me.
Hey, I want to start with a little bit about you and your background, because this is a pretty interesting topic for us to dive deep into science fiction of Mars and space travel. So I want to get a better picture of where you're coming from and what knowledge you're bringing to the table here.
I'm a bit of an odd duck, actually, for NASA. I went to school late after working extensively in a record shop, a CD shop, actually, I should say. We didn't sell records in the 1980s for 6 or so years after I turned 18. And I finally was introduced to an odd college. So St. John's is a weird degree. When you're done, you have, there's so many classes, it's 120 units, I think. you end up with a dual degree in philosophy and the history of math and science, and then a dual minor in classics and comparative literature. And I got a job as a tech person in the 2000, right before the 2000 tech bubble burst, and I was doing configuration of FreeBSD boxes and things like that, Unix stuff, which didn't really match with what the school did, but it matched with my hobbies. And I was coming home pretty early for a startup company, probably right around 5, and I would catch three shows of The Simpsons, okay? But in between 2 of the shows, there was a half-an-hour break, and I would always flip over to the Discovery Channel, and I saw a special on the space shuttle, and I didn't go back to The Simpsons. And I sat there and I thought, is there any reason why I can't go get another degree and go work for NASA? Can't think of one. Okay. So who does aerospace engineering stuff? I mean, MIT comes to mind, but I'm not even sure what state that's in. Oh, that's what the M stands for. Got it. All right, Massachusetts. All right, I'll make an application to that in my spare time and go see if I can learn something about doing aerospace stuff, and that's what I did. I didn't do very well there, and it took me a while to understand why. I think St. John's teaches the scientific mode of thought. Engineering is entirely different. And learning that language and learning why partial credit was important, that sort of thing, was a real challenge for me. But once I got it, I did pretty well. It was a lot of fun learning at MIT. And then I managed to get a job at JPL and worked in technology development there. I did work a little bit on Curiosity, although it wasn't very much, to my regret. But some people that I met invited me to do some work at headquarters, and I ended up working on the Exploration Systems Architecture Study in 2005, which was the first time that we were trying to go back to the moon in the 2000s, the last time before Artemis. Mm-hmm. And so I got to work on Constellation a little bit, and I worked for Scott Pace in PA&E, and they asked me to stay and become a civil servant because, of course, JPLers are technically contractors. And I became a civil servant, worked in PA&E for a few years, and then when the Office of the Chief Technologist was spun up, they asked me to come over and help get NIAC on track, the NASA Innovative Advanced Concepts Program. The program executive was someone I'd known for 10 years at that point, and he was falling behind. There was too much work to do, so he asked me to come in and help, and he made me program manager. And eventually, when he moved up, I took the program executive slot for NIAC, and I've been there ever since. So I've worked about half my career for NIAC.
So I wanna take a step back and continue to look at your whole expansive career, because the topic for today is science fiction, and I know you're a big fan of reading.
Yes, I am. I love reading. I have thousands of books downstairs. I stopped counting the volumes 20 years ago, and for a while I counted board feet. Now I just count how many darn boxes I have to move when I move. And it was a lot. It's a passion. I tend to read more fantasy literature, actually, than I do science fiction. I love science fiction, but there's something about the fantasy genre that really grips me. I think the difference between them really is that science fiction is more about societies, and fantasy novels are more about the individual. And so I tend to identify more strongly with the individuals in the fantasy novels, whereas, the day-to-day work that we do at NASA, in some ways, science fiction inspires us, but in other ways, it kind of makes us look bad. How come we don't have warp drive yet? I mean, we had that in the 60s with Star Trek, right? I mean, what's going on? How come you guys can't even do Star Trek? That was in the 60s. So that sort of inflating of what we think is possible is something we have to struggle with when we describe to the average person how difficult space travel really is, especially for humans. It's insanely difficult, right? One mistake and you lose your crew, and that's not a good day. Yeah. And, a mistake on Star Trek, you lose the red shirt. Everybody else gets back home fine.
That's true. And honestly, I mean,
Yeah.
you see this all the time with particularly science fiction. It's taking maybe a concept, maybe an idea, maybe it's focused on one single thing, maybe consciousness or maybe space travel, just in general. And then what they do is they just say, all right, what can go wrong? And a lot of the narrative is maybe on the society on how things can go wrong. At least that's what I find when because I think I read and watch more shows based on science fiction, maybe more so than on fantasy, at least for me.
Well, for television, I tend to watch a lot of science fiction. I like the sci-fi shows a lot. I haven't yet watched The Expanse, which I haven't started because I kind of like having weekends. And I know I'm not going to have them once I start The Expanse for at least a couple of weekends. But what is it called? There's this one show my wife and I have been watching quite a bit. I'm trying to look it up. The shows are just so gripping and on TV, and there are so many of them now. I think it's really been getting more and more and more. And I think Star Trek back in the 60s and 70s started it all, right? But the reboot as The Next Generation with Patrick Stewart in the 80s was a huge deal, and Sci-Fi Channel starting and everything coming from there. It's just been an explosion of science fiction literature. It's really great.
Yeah, I'm definitely seeing the whole landscape. That was one of the things that I wanted to bring up and this is something that I'm definitely seeing, is I just feel like there's more science fiction, and then even more specifically than that, I'm seeing a lot of science fiction being tied to human spaceflight. Maybe more so than in the past.
Yeah, I think so, and it's been a real pleasure to see it, right? I mean, and what's been really fascinating is to watch it get more realistic as well. I mean, you go back to the late 70s and the release of Star Wars, and we can watch those now and say, for the 70s, we really do see that's pretty good graphics. That the model work and everything, it holds up pretty well. But you look at a modern, I mean, even something from the 1990s, like Babylon 5 with its large space station, right? The graphics that were done even in the 90s were just phenomenal in comparison. And with the explosion of computing that's been happening since the 90s, computers are supercomputers compared to the 2000s. You can have them on your desk now, the supercomputers, and much less than 1990s. And you can do so much with it. 4K, HD, real-time, full ray tracing is here basically now. It's really exciting. The show that I was thinking of that my wife and I are watching right now is Altered Carbon, which is this really fascinating, gritty sort of trying to be as realistic as it possibly can be show about what happens if you can download your brain into a chip at the base of your spine. When you lose your meat body, you can just have that consciousness put into a new meat body, right? And so then you get these people that can change bodies because they're very rich, and they can, the intrigue and the science. But what's really interesting is it's looking at the society that results from having immortality, or essentially immortality, right? And so these societal questions are the big thing, I think, in science fiction. You can see it back in Star Trek. I mean, the Klingons were the other, or some sort of different society, and having constant skirmishes with them and fights over war. They would actually put negative societal actions into the Klingons and then see what happens when they interact with the Federation, and hold up the Federation as the hero. It was really interesting, and there were some challenges with the other, so to speak. Sorry. Anyway.
Yeah,
very rambling.
No, this is perfect, because I think I've started Altered Carbon, but I know I've been watching more Westworld, which explores a lot of those same themes of immortality. So I can absolutely relate, especially with these themes. What is it about science fiction that you think what are some of the good things about science fiction that or things that really draw you in? Is it maybe those societal themes? Is it maybe a little bit of the technology and exploring these different capabilities?
The technology is always a fun thing to watch for me as well. Now, what you said the good side, so I'll keep to the good side for now. One of the techniques that a science fiction author can use is to take a fact and change it, and then try and imagine what a society would look like if that fact was changed, right? So you do a historical fact, say, what would happen if the Third Reich had gotten the bomb first, right? And then you can explore that and see what happens. I think there's a show from Amazon Prime that has that as their theme, sort of, that the Third Reich won the World War II, and what does the world look like, and how does that? So what's really fascinating about science fiction to me is that is reflecting on our own society. All of those things that are in that show or that story are really just pulling out something that exists in our own society and accentuating it, and either making it silly or making it threatening or making it foreboding, or making it wonderful. Like, what if we had warp drive? How would society change if we had a multi-star species, right? So all of those things can be thought about and explored in science fiction that it's hard to do with a contemporary novel.
Now, I know you were focusing a lot on the good, but that did make me think, obviously, I definitely tend to stray towards ideas that maybe I can lock onto and understand. But sometimes if I'm watching a show and I see something that may be either factually inaccurate, or maybe, you take that fact and it spins it maybe the wrong way, it kind of takes me out of it. Those are things that might bother me. I'm sure you have a couple of those as well.
Oh, yeah. There's this great scene in, I think it's Armageddon, where they go and they blow up an asteroid that's going to come. I don't remember what the name of the movie was. They're using the moon. They're having to do something on the moon in this movie, and they use the low gravity of the moon to jump over a ginormous cavern, and then they use the moon's gravity to do a slingshot maneuver to move their ship much faster. Now, both of those things are technically close to real, but to do both of them within 5 minutes of each other, the apparent contradiction, which isn't really there, those like I said, those are both relatively reasonable things. You could use the moon's orbital velocity around the Earth to do a slingshot. It wouldn't be much, but you could do it. And yes, the moon has lower gravity, so you'd be able to jump farther. But when I saw it the first time, it was the juxtaposition of those two things made me think that they were trying to, eat their cake and have it too, right? So, or have your cake and eat it too. But the factual inaccuracies, people don't go to movies with me often. My wife, she doesn't like it because I'll start grumping in the middle of the movie. That's not possible. Everybody likes to joke about the core, right? Yeah, the eight pieces of the ship are all carefully arranged, and then they lose one at a time or whatever it is. And well, if you didn't need all of those pieces of your ship to function, to live, then why did you bring them with you? So,
those major things. See, this is, and I think that's a good lead into this next topic, because I think you probably experienced this maybe a little bit more than most because of your job as in the Innovative Advanced Concepts program. I remember just chatting with you a little bit beforehand, and you called it a very mentally demanding job. And I've explored a little bit of this program, and I think maybe it has to do with, and you can maybe correct me if I'm wrong, I've seen so many different technologies come through. You're just reading idea after idea.
Yeah. We generally get between 200 and 300 proposals per year. And those proposals are from anywhere. So we literally have had garage inventors funded by our program. I know one guy who, in his phase one, he had his optics bench out in his detached garage near the Finger Lakes of New York State. And he went on to win a phase two, and he's working with the university, has a real lab now. But it's interesting because you have to be able to distinguish fact from fiction, science fact from science fiction. But because the stated goal of NIAC is to invest in technologies that are 10 or 20 or even 30 or more years from being used first, you kind of have to have some suspension of disbelief. For instance, we funded one gentleman to talk about how you would build a new space station with an architectural technique called tensegrity, which is a very odd technique invented by Buckminster Fuller back in the 1950s. And I can't describe what tensegrity is. If somebody's interested, they should go look it up. You can even buy little squish toys for babies that are tensegrity toys. Essentially, what it does is it allows you to have all of your architectural pieces that are in tension only in tension, and the tension is all along one line of force. And all of your pieces that are in compression are only in compression, and all of the compression follows one line of force. So you can optimize your architectural structure very, very finely. And in fact, you can provide the same amount of strength as a steel beam with something on the order of 90% less mass of that steel beam. Now, that line of force can't really change. If it does, it'll squish your tower funny. So it's almost never used for anything but art here on Earth. But this architectural person said, you know what this would be really good for is a space habitat. You could make a giant rotating space station and collapse it down into essentially an IKEA flat pack when you launch it. And then it will self-expand when it's out there. You can then, if you design this thing correctly, add more material, more of the compressive elements and the tension elements, and expand the size of the habitat. And he came up with this idea of growing a habitat by doing, essentially, other people will hopefully someday start in-space mining. And the most valuable thing that they will be able to mine from asteroids and comets is water. But the mining process is going to leave a lot of stuff left over. Well, with only a small amount of processing of that stuff, you could make more tensegrity components. And so essentially the slag that's left over becomes raw materials for enlarging your habitat size. And so he came up with an architecture by the end of his phase one work where with one single Falcon Heavy launch, you could have the internal volume of about half the space station, the International Space Station. Now, that internal volume, of course, is all in one piece, not divided up by modules and all of that because of the way that he grew it. So it might be less usable because, as you know, the International Space Station has every surface of every wall is useful, and they have a lot of those walls and a lot of cabins, and so they're able to do a lot of work. And this would not be as useful for science, but it might be a nice hotel, right? So he came up with the idea of actually trying to build this thing much earlier than the 50 or more years that I expected it to take, and then selling flats on it to help fund the building of it. And he's gotten a NIAC Phase 2, and he's moved on to trying to finish that up and then look for investors, and he's got a few interested people, which is way farther than I thought he would get. And so how do you distinguish something that could become science fact 50 years down the road from something that is truly science fiction? And that is mentally exhausting. And so to go through 200 to 300 of these papers every year and then select the 16 or so that we are allowed to fund is my real challenge, my real job for the year. And then, of course, running the program, keeping those fellows, we call them NIAC fellows, functioning and getting them whatever they need, and handling all the paperwork for them is the rest of my job. And by the way, we just made our final selections for the year, and hopefully by the time that this podcast goes live, you'll be able to see the press release on what our new concepts are.
Wonderful. Okay, so if I were to summarize this program, the NASA Innovative Advanced Concepts program, you're looking at all of these all of these, maybe what some would call crazy ideas that are
Mhm.
maybe in its infancy and you're looking for results way in the future. You narrow it down, and it sounds like there's different phases based on maybe maturity, it sounded like?
So, no, actually, I should describe the program in its most basic format because anyone in the United States is able to apply to it. And so that's really important to know. If you're a civil servant, you can still apply for a NIAC grant. If you're a university person, you can apply for a NIAC grant. If you have your own small business, you can apply for a NIAC grant. If you're an individual, you can apply for a NIAC grant, but you have to have a small business to receive the money. So you would have to start a small business. We do 3 phases of design. The first is our phase 1, which is $125,000 over 9 months to produce a white paper by the end showing that the idea that you came up with is feasible given a certain few assumptions and a good idea. As in, you would want to show us that your new in-space thruster, whatever it is, or, I'm making this up when I say in-space thruster. It could be anything. But let's take in-space thruster because that's an excellent example of why NIAC is the way that it is. You show us the in-space thruster. Let's just say that it was a new fusion in-space thruster. So really far advanced concept that may never happen. But let's think about it from an engineering perspective here, because we don't ask at NIAC for you to tell us about your thruster so much as what mission your thruster could do. And we do that for a very specific reason. We want to see mission-level impacts of your new technology. And so if you say, I've got this new in-space fusion thruster, it's the best thing since sliced bread, that's the best thing for in-space thruster that's ever been, and then you go and you do your analysis, you might find that your fusion thruster works just fine, but it produces a lot of heat. And because it produces so much heat, you need to have gigantic radiators on your spacecraft. And in fact, those radiators mass so much that your beautiful fusion in-space thruster is less effective than current chemical propulsion is. And so we ask for all proposers to provide us with a back-of-the-envelope equation showing something at a system level or something anyway, showing that you are thinking about the mission concept and how this might actually be used. And so after 9 months, a quick turn of the analysis crank showing NASA that your idea actually might work in a spacecraft, okay? Or we are open to aeronautics as well, so in an aircraft would work as well. Then there's a second phase for the best concepts. You can imagine phase 1 is TRL 1 to 2 starting and 2 to 3 ending. Technology readiness level. If you aren't familiar with that, then that's something you can look up, NASA TRL. TRL 1 is technically, you don't know how this thing would be used, but you have an idea. So none of the NIAC ideas technically fit into TRL 1. But because they're 30 to 40 to 50 years out, sometimes we often will refer to it that way. TRL 3 is you're ready to start testing on a benchtop to see if the physics work for your idea. And I might get some of these slightly wrong because I don't refer to the TRL list every day, but please go look it up and you can see what the TRL list is. And so phase 2 is for the most promising phase 1 concepts. They've done that turn of the analysis crank, and it looks promising. Your radiators aren't going to be too large to invalidate, or so large that they invalidate your design, right? So we pick about 6. So we get 12 to 16 new phase 1s every year. And every year we get about 6 to 7 phase 2s. Phase 2s are a 2-year study with a total of $500,000 spent over the 2 years. And generally it'll raise the TRL another notch. For those that are unfamiliar with the TRL scale, I can tell you that 1 is your initial concept idea. You've had your light bulb go off in your head. 9 means that it's flown in space and it's a proven technology. And so the range goes from 1 to 9. And so TRL, we would imagine a phase 2 entering TRL 3 or so and exiting at TRL 4 or so or 5. And of course, it's a range. Each individual concept is different. A lot of folks, when they first hear about NIAC, they think, oh gosh, well, that's a nice thing. I'm sure that they produce lots of white papers that are very interesting, and that's true. A lot of times what we get out of a study is a white paper. But we also have exceptional performers in the program, just like anywhere, I suppose. But I haven't really had a single fellow come through that didn't shine. And our highest performers, in the middle of a phase 2, we have a midterm review to make sure that the government money is being well spent and not, buying somebody a nice new car or something. So we had our midterms. This is 8 years ago now for our first phase 2s in 2012. And we had one of our performers bring 3 separate functional robots to their midterm, close to final, not flight hardware, of course, but close to final configuration that could be tested for flight hardware. It was really just astounding. I've seen potential low-gravity rovers. I don't know what to call them. They're not really rovers. They're hoppers. But performers NIAC fellows have brought robots that could hop on a comet, that actually are able to hop in full Earth gravity as well. They just don't hop as far, maybe 2 or 3 inches or 4 or 5 if you spin them up really fast. So, that particular one was Marco Pavone from Stanford University, and he came up with this really innovative thing. It's about the size of a CubeSat, maybe 1.5 CubeSats on each side, so 15 centimeters instead of 10 on a side. And it's a little box, and he put control moment gyros in there, and he would spin the gyros up really fast and then break them suddenly, very, very hard. And, of course, that transfers the angular momentum from the gyro to the frame, and then the frame pushes against the table and flops over. Okay, and depending on how fast you spin those those gyros, you can actually have the thing fly. And if you do it on a comet or a small body like Phobos, was what he was looking at, you would be able to move those rovers around on the surface quite accurately and quite long distances based on how they break those gyros. It's really interesting. And he was coming for his midterm review, and they were walking through the Air and Space Museum here in Washington, D.C., because that's what you do when you come to NASA headquarters, is you stop the day before to go through the Air and Space Museum. And they were carrying their robot with them, and some kid said, hey, what's that? And they said, it's a robot that we're building for NASA. And they said, really? Can we see? And within about 10 minutes, they had checked with the security guards first, and they were giving a demonstration of their NIAC concept in front of the Apollo lunar lander, and they had a crowd of about 50 people all watching them test their rover for Phobos there on the floor of the museum. So it was really great concept.
Wow.
Really fun. So so NIAC people are like that. They're bootstraps type of people. But here these people were doing public outreach for NASA with 50 people watching. Just really great stuff.
That's fantastic. What I like about what you're describing about this program is it's called advanced concepts because and I think you spelled it out really nicely, because you're thinking so far out into the future but there still is, even at the ground level, some element of practicality in what may be considered a wild idea, but it is grounded in practicality.
Yes, it is. In almost every case. Now we try to toe the line. We actually do try to go up to the edge of science fiction. I can give you a good example of that. But before I do that, let me tell you about the third phase of study, which we just added.
Oh, yeah, we missed it. Totally. Yeah, it was
fine. Phase 3 is for technologies that have real promise and have real interest from other programs or other people. It's not necessary to have, for instance, the Science Mission Directorate saying, we will give you money if you have a Phase 3. And we will implement your idea in a future mission. It's possible that SpaceX would be interested, and we would count that, or Blue Origin, or some other government agency like DARPA could be interested in follow-on funding. If you have other people interested in picking up your technology after the end of a Phase 2, you can apply for a Phase 3. And a Phase 3 is 2 years with $2 million total funding to really eliminate the risks that the other party sees in your technology so that you can then go on and have it picked up. Hopefully. That's the purpose of a phase 3, is actually bridging the gap to implementation. And on the TRL scale, we would expect you to get to TRL 5 or 6, which is subsystem testing in a relevant environment, I believe, although 6 to 7 is often argued about at length during meetings. So don't quote me on that TRL definition. So, and we've only had 2 phase 3s so far, and both of them were very focused on implementation. So hopefully we'll see something in another year and a half about how well they're doing. So an example of edge of science fiction thinking for NIAC would be torpor. Okay, so what is torpor? We funded a study a few years back on astronaut torpor. So you've often heard the term in science fiction cryosleep. The basic idea is, in science fiction, the astronauts who are on the ship cool their bodies down through a mechanism on the spaceship and go into cryosleep, and then they wake up when the computer warms them back up at their destination. This has been talked about in science fiction for decades and decades and decades. No one, as far as we can tell, had ever actually designed a human-rated spacecraft, even at a very preliminary level of design, to find out if that would save mass or not. It is conceivable that because you have this extensive computer system monitoring, and it's all automated, autonomous computer system, attending to the humans that are in cryosleep, or I'll get to why we call it torpor in a second, that you have to add so much mass for that, and you have to add so much work on the computers that by the time that you're done, the system is larger, less efficient, and more expensive than just building a normal spacecraft. Okay? Nobody had ever done that study. Now, what was interesting when these folks from SpaceWorks, that's the SpaceWorks Engineering is the company that proposed this work, Dr. Bradford was the fellow, the NIAC fellow. When they proposed, they were able to quote to us, well, we do torpor every day in the medical community. Someone who has a heart attack at an inopportune time, let's just say that the local cardiac surgeon is out on Fiji on their vacation, whatever the reason is, they can't get to the hospital until the next day or 2 days from now. It is a common medical practice now to take this person who has had a cardiac arrest, has a damaged heart, and cool them down, put them into torpor, a cryosleep, if you will. And you can do this with a few drugs, I believe. There are other ways of doing it, they found relatively reasonably. You can administer some of these drugs just through the nasal cavity. You just plug in a breather, and the person will go to sleep, and their core temperature will fall 2 to 3 degrees Celsius, and that reduces their metabolism by something on the order of 60%. And that keeps their heart from continuous damage. The cold helps them as well. And I actually have a personal story about this. My third child was born almost 2 years ago, unexpectedly, here in the very room that I'm sitting in, at home, and it took us a little while to get her to the hospital. And she had meconium aspiration, which damages the lungs and the womb, and we didn't know that. And by the time that we got her to the hospital, about 45 minutes later, she had her oxygen saturation in her blood go down to 29, which is brain damage level territory.
Oh, wow.
And yeah, it was very, very scary at the time. In fact, it was possible that she could have died. And that is kind of what the expected outcome is in that situation when you have a pulse ox at 29, at oxygen saturation level 29, you kind of expect the person to have extensive brain damage. Well, it turns out that with newborns, if you put them into torpor for a couple of days after a low oxygen saturation event, that the brain damage that occurs can heal itself. It turns out that the damage is preliminary, but the swelling and the resulting damage from the swelling inside of the brain is what makes the scarring that causes permanent damage. And so they put our daughter in torpor for almost 3 days. And I'm happy to say she's essentially completely normal. There's no permanent effects that we've seen from this event. She's learning, talking, walking, doing everything loudly and annoyingly, just like her siblings. So torpor is something that we do every day, literally at hospitals, probably near every listener that's listening to this. It's done in multiple countries, and it has been done experimentally for up to 14 days. And so John Bradford, when he proposed, he said, what we want to do is take the Mars Design Reference Architecture 5.0, which is a public document that defines one way that NASA could go to Mars and come back with astronauts, and do a spacecraft for the planetary transfer that has 4 astronauts in torpor, alternating every 14 days. Someone new would wake up, or it was something like every 5 days, so that rotating so that every person slept for 14 days in torpor, and then they would have 3 or 4 days awake, and then they would go back to sleep in torpor for 14 days, since that is current state-of-the-art torpor. Okay? Mm-hmm. And they said, so one person is always awake in case there's an emergency and things need to happen quickly. And what we want to do is see what the spacecraft design would look like if we did this. And we'll do some work on the torpor as well, just to make sure that it would be okay in space. But the main thing is, would a spacecraft actually be feasible, and would it be better? And when they were done with their study, they did a pretty decent engineering analysis of what a ship would look like, given the assumptions that they made. And they came out with something on the order of 40% less initial mass in low Earth orbit at the end of their study. And so is this science fiction, or is science fact, or somewhere in between? And I can't answer that for you really right now, because there are some pretty serious compromises that the astronauts would have to undergo. They would need to have a feeding tube put into their stomach. It's called a PEG tube. It's very normal. There are people that have PEG tubes at home, and they actually take nutrients or vitamins in or medicines in through their PEG tube. It's not a big deal, but it might be a big deal in space. We don't know. We haven't done this, right? So in the end, this is a really interesting study, and probably not something that NASA will do in the future, but it's nice to have that study available in the literature and quotable and referenceable. And that's another thing about the NIAC program that's very interesting. We take all of our final reports, and barring any patents or other sort of secret sauce that a company might need to keep secret to maintain a competitive advantage, we actually post the final reports up on the NASA website. You can see all of the released final reports at www.nasa.gov/NIAC. And then you can click on the completed studies link or studies link, and anything that's older than about a year should have its has been completed for more than a year, should have its information up there available for download and reading. And it takes us a while, because when we put something on a government website, it needs to be readable by a screen reader. We need to be able to use equations and tables and graphics, and all of those need to be readable by a screen reader. And so the 508 compliance, as it's called, to make sure that it's readable by a screen reader, is extensive. And we also need to make sure there's no ITAR violations. We don't want to be violating a law about we don't want to arm our enemies of the state. So ITAR, the international, export control, ITAR, all of that has to be checked for. So it takes us some time after the report's been provided to us before it's up on the website. But I think we have over 100 up there at the moment. So it's a really neat program doing some really great work that has actually made a difference. We now have a Science Mission Directorate mission called GUSTO, entirely based on one of the NIAC ideas, which was radio astronomy can be done from the inside of a weather balloon. You put another weather balloon in, a small one that's spherical, illuminize half of that small interior balloon. And when the weather balloon gets up to 110,000 feet, you have to have a secondary mirror that has a spherical corrector on it. But your balloon within a balloon is up above 98% of the atmosphere, or even 99% of the atmosphere, and can actually do radio astronomy through the 2 layers of mylar with very low losses, because the mylar is essentially transparent in some bands of the radio spectrum. So for $35 million, they're going to be able to, hopefully, in 2021, in December, fly a 5-meter reflector for a total cost of $35 million, which is really exciting. So.
Wow.
Yeah, it's really cool stuff.
It's across the board, it sounds like. It sounds like there's, I mean, you're talking about multiple different disciplines. You're talking about, human biology. You're talking about space stations, like actual structures. You gave an example about propulsion. There's so many, it seems like you're kind of across the board here when it comes to the areas that you're thinking about.
Yes, and that's one of the reasons why, as we started the whole discussion about NIAC, it can be mentally exhausting. Why I don't read as much science fiction anymore is I'm reading so much science at work, and the television seems to work pretty well for science fiction for me. So.
Well, I'd hate to ask you for more, but I am interested in ones that are particularly interesting for a Mars mission. And it sounds like that one that's really close to science fiction is something that's just interesting. But I know of one in particular, and maybe it's something that's, I have heard of this before. I think it's called a hypersonic inflatable aerodynamic decelerator. And it has something to do with... it's pretty difficult when you're thinking about a Mars mission, the entry, descent, and landing phase. So this is a cool technology for that.
So there's several NIAC studies that have been for entry, descent, and landing, EDL, as they like to say. HIAD, the Hypersonic Inflatable Aerodynamic Decelerator, is an actual STMD technology demonstrator mission, TDM.
Oh.
And that was essentially instead of using a parachute, which there are a lot of challenges with parachutes. I don't know if you've ever watched the documentary that PBS did on the MER rovers and the parachutes and the inflatable bags that cushioned the rovers when they landed, Spirit and Opportunity. But the Adam Stelzner, Dr. Stelzner, was the person in charge of the parachutes at the time, and they had one of the parachutes, when they first inflated it in test, just shred completely into pieces. This is after they had, these are the same people that had worked on Pathfinder. So, the package for Pathfinder was almost the same mass as the MER rovers. Why should the parachute have been so different? And then after they got the shredding fixed, the next test that they did, they got what's called squidding, when the parachute doesn't fully inflate. And they solved all of those problems and had an absolutely flawless and spectacular landing for both Spirit and Opportunity, really, truly tremendous mission. But there's another way of doing a deceleration with aerodynamics, and that is you inflate what's called a balute. Essentially, you have a big balloon inflate on your vehicle instead of having guy wires holding a chute out in front of you. And you can inflate them very quickly, like the airbags for Spirit and Opportunity. They can be inflated with a rocket motor. The exhaust will inflate these things very, very quickly. And so the HIAD was a test that we did in Earth's upper atmosphere, up where it's about Mars thickness, where you launch a rocket up and then you fire a secondary rocket, inflate your decelerator at the appropriate level of atmosphere in Earth's atmosphere and at the appropriate speed so that you can actually test in relevant conditions. And it worked pretty well. HIAD was a great mission. It didn't work 100%, but it did exactly what we needed to do to be able to hopefully do this at Mars someday. Some of the NIACs for this are really interesting. Of course, HIAD was fascinating, and hundreds and hundreds of people worked on it. A great mission. So I'm not saying that wasn't interesting. But one of the most interesting ones I think we've had for NIAC is, well, you could actually have a magnet replace a parachute or a balute. And the way that works is if you have a very strong electromagnet, and then you inject some plasma, a charged plasma, into this magnetic field that starts bouncing around. And those charged particles hit the neutral particles that are in the atmosphere of Mars, and they knock that atmosphere apart. So the neutral particles become part of the plasma. They get broken apart. The electron leaves. You get the proton. Yes. And so those will interact with your magnetic field. The particle momentum exchange will slow your plasma down, and the plasma will pull on your magnetic field lines and then slow your spacecraft down. But depending on the kind of electromagnet that you bring, you can actually make a plasma structure that is very large compared to a parachute or a balut. And you can use it way up higher in the atmosphere. When the atmosphere is more tenuous, it's actually larger. And so you could slow down with a larger, magnetic balut, if you will, for longer and make it safer for a larger payload to slow down. But it does take a lot longer to slow down. So you have to hit the top of the atmosphere and start using it early and have a shallower angle of descent and everything. It's fascinating, and somebody did study that. That was David Kirtley of MSNV at the time. That was a company, or is a company, up in the Seattle area. And he worked with some Langley folks. Bob Moses was one of the folks down at Langley that worked with him on that. So that was really fascinating, and it appears to be real. This actually works. They inflated a magnetic balut in a thermal vac chamber and fired a rocket motor at it and had that plasma grow in size and have momentum exchange that they were able to measure. It really looks like it could work. It's exciting stuff.
It seems like the things that the examples that you're bringing up and some of the things that seem to excite you the most, from what I'm gauging, they're just wild ideas, things that are completely out of the box. But it seems like what's really exciting is there is a level of promise to a lot of these ideas. Maybe not used in full, but just it's enough to make you curious on, maybe this is something that can actually help with human spaceflight.
Oh, yeah. There's a lot of things that have come through over the years. NIAC has had a storied past, actually. It was started as an external institute run by the USRA. Dr. Bob Casanova was the program manager outside, and he had complete control over funding what he chose to fund. And he often would say, I'm not going to fund something unless somebody around the table tells me that it's impossible. They have to. I have to think they're wrong, of course, but somebody's got to say this is so hard that it's impossible, or it's not worth NIAC to fund. So that ran for 9 years. That program ran for 9 years, and it was shut down in 2007 with the Constellation program, trying to get back to the moon, and there was no way to steer that program to help get back to the moon. We got it restarted again in 2011. But made it open to everybody instead of making it an external research organization. Now NASA people can propose to it, and it's a great thing that we did, because there's a lot of people at NASA that have these creative thoughts that have no way to get them considered for anything, because, by golly, we're going to build Artemis right now, and that's what we're going to do, and that's the right thing to do. But maybe they have an idea of where else we could go on the moon, or a different technology that we could do once we get there, or how to explore robotically before we send the humans, that sort of thing. So all of this stuff is, to me, what gets really exciting is this sort of combination, as you're saying, of really far out stuff, but that might be useful right now, that it makes you think differently. And I think that's a big part of what NIAC is it helps us all think a little bit differently, be a little bit more excited.
When you hear a lot of these proposals come in, I'm wondering what inspires some of these folks to come up with these ideas. Maybe it's something through their own research that they just put several elements together. That medical procedure of putting someone in almost cryo sleep and mixing that with the structure and mass of building a spacecraft. Those are two ideas that just sort of slam together. Maybe it's from watching or reading science fiction. Do they ever tell you stories of where they get these ideas?
Yeah, they do. I think a lot of them actually have come out of NIAC itself. We force all of our fellows, I shouldn't really say force, we invite all of our fellows to get together once a year, and hopefully we'll be able to do it this year, in person for their midterm report outs. And so every technology project is supposed to give a report about halfway through on their progress so far. And so we get everybody together and we have them give these reports to the program office in front of the whole community. And every year I'll be eating breakfast down in the hotel restaurant or something, and someone will come up to me and they'll have bags under their eyes and their hair will be a little bit mussed up. And Jason, I can't thank you enough for this meeting, because I've been up since last night, and we've been working together with these two fellows, and I have gotten together and been talking about how to combine our ideas into something really new and useful. And I'm going to go up and shower before the meeting, But I think there's a lot of stories in the history of science about how innovation happens. And I think there's something to this sort of, NIAC is open to all different technology areas, and that makes a difference, because when you get these people together, they have to think outside of the box to understand each other's ideas. They have to think out of their comfort zone. If you've been doing in-space propulsion for 27 years or however long your career has been, and you are forced to look at somebody's new spacesuit, and you see that some of the materials that they're using for their spacesuit are actually materials that you've used for years in the cladding of your engine, your ion engine, or something of the sort, right? You make these connections across disciplinary lines, and it makes people think creatively. There's an old story about Niels Bohr, who was the person who came up with the way that we think of the atom today, with a central nucleus and electron shells outside. And he was exciting electrons. This is just after Rutherford had really come up with the idea of the electron shells. So Bohr wasn't working on the actual model of the atom. He was working on why electrons seemed to have specific places that they liked to go around the nucleus. So he was exciting these atoms, and he would see light coming off as the electron fell back down from one orbit to another. It would release a photon. It would release some energy. And he noticed that the wavelengths of that energy that was released was always in a whole number ratio to itself. So you might see something come off with a wavelength, and I'll make this up because it's easy to understand, of 1, okay? And then sometimes, though, you would see something come off with a wavelength of 1/2 or 1/3 or 1/4 or 1/5 or 1/6. But you would never see anything that didn't fit into that neat fraction of 1 over n. It always fit into that. And he said, you know what? That's like a violin string. I love music. He never played instruments himself, but he had a brother-in-law that played the violin. He would invite him over to play the violin as often as he could, because he just loved music so very much. And he made the connection. That's like a vibrating string. A string vibrates in its whole mode, and then its half mode, and its 1/3 mode. You could remember when you were a kid and you played with strings and you made them into lobes by spinning them around and everything. Or if you were in physics and you had a spring and you saw how the vibrational modes were for a string, right? So this is clearly the electron is vibrating, and it has to finish a number of vibrations before it can move to a new shell. So it can only be in distances that have the right distance for those vibrations to complete. And that's how the electron shell model of the atom was created, is because Niels Bohr loved music. And so these different disciplines combining together, I think, is where you get the real innovation. It's just super exciting. So
yeah, and it seems like maybe it's almost a passive thing. It sounds like maybe you just love music and you have an understanding of a different field, and maybe just slowly you just start to realize the connections between these things, because you're into these two things that maybe not a lot of people are into, and all these ideas maybe come together in your head maybe better than most. So I think the lesson here is maybe capitalize on that. If you find something, then it might be worth pursuing.
Yeah, always. And having an avocation is helpful for that. But the other key thing, I think, is understanding when something is useful, right? And that's something I'm not sure how to do. But when you see something and apply it to another discipline, understanding that what you're doing is useful and helpful, that's another challenge entirely. And that's where the bulk of my work is trying to understand what these people are doing and determining whether, in the original program, Dr. Deva Newman was a fellow, and she came up with this very interesting spacesuit. She said that you can draw lines on your arm, and if you draw them in just the right way, no matter how you move your hand and arm, that line will not change length. Okay, you might connect a spot on your wrist up to a spot on your elbow. And no matter how you gyrate or move, that particular line, while it might shift slightly, it won't gain length or shrink. The skin is flexible. Some parts of it will stretch, some parts of it compress. Obviously, in between the stretching and the compression parts, there's a line that doesn't change length. She said, what if you took a Lycra spacesuit and you stitched Kevlar in on those lines of non-extension? I'll bet you could make a spacesuit, that didn't have to be inflated to hold pressure against your skin. And she did that as part of a NIAC in the first program. And it worked. She was able to make a brand new spacesuit that nobody had really thought of before. Well, lots of people had thought about it. You can actually see pictures of suits like this in science fiction, but she was able to make one that probably would work. And it's a really amazing and beautiful suit. It's incredibly difficult to manufacture, I understand. And that may be why we never bothered to do it. I'm not sure. But she, did a really good job. She was a professor at MIT. She did great work. She managed to make some spacesuits that seemed to work really well, at least on the ground and in testing. And eventually she became deputy administrator of NASA. So that's something, too. A pretty neat thing that she came up with. And it helped her career as an academic, and it helped her understand space in a different way. So really cool stuff.
Yeah. And honestly, for conversations I've had on this podcast, this is definitely one that had my mind more challenged, thinking about these open ideas. I talked to a lot of folks that were talking about real flight hardware, so just taking the time to think about really unique and odd maybe ideas, and how there's a whole program at NASA dedicated to inspiring people to pursue those ideas is it's truly amazing. Jason, I really appreciate you coming on and going through some of these wild ideas with me. This was really, really fun.
Absolutely. Thank you so much for the opportunity to have a great conversation like this. I appreciate it.
Houston, go ahead. Stop of the space shuttle.
Roger, 0J, and I feel fine.
Shuttle has cleared the tower.
Became a feat for all mankind.
It's actually a huge honor to break a record like this.
Not because they are easy, but because they are hard.
Never Houston, welcome to space.
Hey, thanks for sticking around. Really crazy ideas we went through with Jason Derleth that actually just might work for a Mars mission. Very interesting stuff. I hope you stay tuned because this is sort of kicking off what we'll try to do is a Mars episode at the first of every month. So this will be our second. We had Michelle Rucker's episode last month. Jason Derleth kicks off the second one, and we'll try to continue it for as long as we can come up with some of these ideas. If you have suggestions, please send them along using the hashtag AskNASA on Facebook, Twitter, and Instagram. We're on the NASA Johnson Space Center pages of all of those platforms. Pick your favorite one, use the hashtag AskNASA, submit an idea, something about a Mars mission if you want, or any other topic. Just make sure to mention it's for Houston. We have a podcast. Thanks for sticking around. This was the first episode we recorded in quarantine during the COVID-19 pandemic. So thanks for sticking around through some of the little sounds you might have been hearing in the background. We're all recording from home, so thanks for sticking with us. This episode was recorded on April 3rd, 2020. Thanks to Alex Perryman, Pat Ryan, Norm Moran, Belinda Polito, Jennifer Hernandez, and Michelle Rucker. Thanks again to Jason Derleth for taking the time to come on the show. Give us a rating and some feedback on whatever platform you're listening to us on, and tell us what you think of the show. We'll be back next week. Houston, we have a podcast. Welcome to the official podcast of the NASA Johnson Space Center, episode 151, Rendezvous with Mars. I'm Gary Jordan, and I'll be your host today. On this podcast, we bring in the experts, scientists, engineers, astronauts, all to let you know what's going on in the world of human spaceflight. We're continuing our Mars monthly series with Patrick Chai, PhD, who humbly requested to be referred to as an aerospace engineer at Langley Research Center in Virginia, but most would call him a rocket scientist. Patrick hones in on the challenges and needs for getting to Mars. The journey from Earth to Mars will be long, somewhere on the order of 9 months. And with that comes a series of challenges, some complicated orbital mechanics, and a whole range of options that consider things like propulsion, duration, timing, staging, and more. Yes, thanks to probes and rovers of the past, we've landed on Mars, but a human landing will be like nothing else before. The transport will have to be much larger. And with humans on board, you're limited on the kinds of routes you can take to get to Mars. Sounds like a simple consideration. Yes, of course there will be humans, but it makes things a lot harder. Buckle up, everybody, and all aboard to the Red Planet. Here we go, the challenges and range of options on how to rendezvous with Mars with Patrick Chai. Enjoy.
T-minus 5 seconds and counting. Mark. Launch commit lights are correct.
Here she goes. Houston, we have a podcast.
Patrick, thanks so much for coming on Houston. We have a podcast today.
Thanks for having me.
This is a really interesting and intricate discussion we're going to have about what it takes to actually get to Mars. So I might go a little bit off track, but you're going to have to steer me to Mars in the right way. Tell me about your background and what got you to the path where you're thinking about Mars rendezvous.
Well, I haven't been at NASA very long. I started in the fall of 2014. I was a graduate student at Langley as well, doing some system analysis for different refueling options. So I was a grad student. So I got my PhD from Georgia Tech, and Georgia Tech has a program at Langley associated with the National Institute of Aerospace, where grad students can be on site there at Langley doing research with folks. And so it kind of gravitated me toward doing system analysis. So that's how I ended up applying for a job at the branch I am in, which is the Space Mission Analysis branch. And once I started there, that's back when there was a big effort to defining what then was called the Evolvable Mars campaign as part of President Obama's a flexible path definition, going to the asteroids and then, having multiple paths getting human to Mars. So I started doing a lot of the trajectory work for that Evolvable Mars campaign, and doing the definitions of how to, all the different mission opportunities and how much propellant it would take if we have, different payloads and things like that. So that kind of evolved into me kind of being the lead of the trajectory analysis team there for all the Mars stuff, and now I'm leading the Mars integration group here at NASA Langley. But I still want to do trajectory work because that's the most important. That's the exciting things that I like to do. Leading team is great, but it's like one of those curse. You move up and you become management, and they don't let you do exciting work anymore.
You have to delegate.
Yeah, exactly. It's hard, man. Yeah. Learning how to delegate is a hard thing to do.
Yeah, especially when you want to do.
Exactly.
You want to get your hands dirty.
So
you mentioned, you alluded to a few different things in your description of what you're thinking about. You're thinking about systems. You're thinking about trajectories. What are these different elements that you're considering when you're thinking, how do we get to Mars?
So for what we're thinking about here, it's always sending crew to Mars, right? So we have a propulsion element that you need some sort of propulsion element to get your crew to and from Mars, right? And the payload that you need to deliver. So typically you have very traditionally you have a chemical stage, and so you have kind of like a regular rocket. You have fuel and oxidizer, and they come into a combustion chamber, and they combust, and then you exhaust that out of the nozzle, and that's how you push things, right? And for Mars, you're either pushing the deep space habitat where the crew lives in, or a payload, which is what we call cargo, which is the lander that you need to land things on Mars surface.
Okay,
And
so you're thinking about the energy, the type of energy it takes to actually get to Mars,
Yeah,
and you're
and
thinking
so-
about what you're going to attach to that energy.
Yeah, and so if for the integrated stack, you have your propulsion elements and you have a payload, and you have to be able to get all those things put together in orbit, and then you send that to Mars, and not only you have to send it to Mars, it has to have enough energy for you to come back too. So you think about a big rocket, as a reference, like a big rocket you're launching from Cape Canaveral. That is a very short distance that it has to do comparatively to where we're needing to go to Mars. So you can imagine the energy that it would need to go all the way to Mars. It's pretty significant.
Yeah. So what's the difference when you're thinking? We're talking at the system level now. We're talking about what you need to actually build to get to Mars. What differs when you add the human element?
When you had the human element, it's kind of different. Yeah. So if you think about the things we've sent to Mars, all the rovers and things like that, those systems have a lifetime, right? But it's electronics. It's powered by battery or solar arrays or whatnot. They can take a much slower route to Mars, which much more energy efficient, right? When you have a crew on board, you have other consideration because if you have a longer duration in space, that means you have to bring more food. That means you have to have bigger space for the crew. You have to have exercise equipment for the crew. So what that actually translates to is you have more payload, you have more mass, so you have to push, you're pushing more things, and that, we call it the tyranny of the rocket equation. It's an exponential relationship. So you add 1 kilogram or 1 pound of payload, it's not equivalent to 1 pound of propellant. It's a much bigger amount. So you can add up really quick. So for human mission, and a little bit for the robotic too, it's all about minimizing that payload mass as much as possible. And these rovers that that JPL and is sending to Mars, I mean, they are very slimmed down, even though they're very beefy and they're very reliable. But they all are always looking for different ways to do, manufacturing and fabrications of these components to minimize the weight, because weight is everything in space.
Yeah. Yeah, so I guess maybe this might be a ridiculous question, but does thinking about having larger systems to get to Mars change your trajectory or your possibilities of how to get there?
It doesn't really change the trajectory, maybe a little bit, but it changes the way you think about how to get to those trajectory. So everything we've sent to Mars so far, you're thinking about these, basically your traditional rocket, and these are, we're getting much more efficient with them, but they're very, I won't say rudimentary, but these are, systems that we've been using for decades, right? And they have their limits in terms of how energy efficient, how much, what we call specific impulse that it can deliver, and specifically what measures kind of the how much energy you can get out of the same amount of propellant. So the higher higher that specific impulse is, the better your system at being efficient. So your traditional rocket, you're looking at maybe 300 to 400 seconds worth of specific impulse, and there's a whole derivation of equation. I don't exactly know why they use seconds as the unit, but it falls out of the equation. But for a traditional chemical, you're looking at 300 to 400 seconds of specific impulse, and with starting to think about some of these other kind of lower thrust and higher energy propulsion systems, like the solar electric propulsion or a nuclear electric propulsion systems that can get you up to 3,000 to 4,000 seconds worth of specific impulse, so an increase of tenfold. The drawback of that is you ended up having to stretch your in-space duration longer, because it naturally is a lower thrust propulsion system. So that's always the battle. You have a low thrust and a high thrust system. A high thrust system kind of is a really big kick to get you out, and you can do another kick to kind of slow you down at Mars, and that's relatively fast. Low thrust, you kind of just like putzing along, for a much longer duration, but ultimately it saves you a lot of propellant, and it's much more robust if you increase your payload mass by a significant amount. It's much more robust to be able to absorb some of that growth. So.
Oh, okay. So there's a lot of different factors you're considering.
Yeah, and what actually we have been working in the last 3 or 4 years is actually kind of marrying the two. And we've been working on what we call a hybrid propulsion system, and it has both components. It has a high thrust and a low thrust system. So you use the high thrust when you're near planets where they are actually most effective, and because you have to, no matter what, you have a long duration transit out to Mars and back anyway. So you might as well use some of that time to do some thrusting and do some maneuvering. And we found that the system that we've kind of been analyzing has some advantages and some disadvantages, but that's how all this and that's the importance, I think, from what we always harp on from our branch, the system analysis perspective. We have to be able to understand the behavior of the system, especially under uncertainty and under changing requirements and that, to understand what you're actually selecting. You can't just say, oh, because we have this very, very tiny optimized point design, we're going to select this propulsion option. Well, what if your design changes a little bit? How sensitive your system is to that change, and we need to have a better understanding of all that before we're able to make really informed decisions.
So, I mean, the hybrid approach sounds very reasonable because you're considering the flexibility. Naturally, when it comes to spaceflight, with flexibility comes mass. Now you're talking about two different propulsion systems.
Yeah, actually, it's kind of, it's actually less in terms of mass. It's more on the complexity side.
Interesting.
In terms of mass, given the same payload and the propulsion system, it depends on the trajectory you fly. The chemical is going to be the heaviest, and then the full EP is going to be the lightest. But you trade time with that too, right? The big rocket will get you there the fastest, but the slow boat electric propulsion will get there much slower. So we're trying to for instance. We have some planetary probes that are flying out there that uses electric propulsion, and they've been very successful in doing that. But these things take years and years to get to wherever they're going, and so it's great for the planetary probe, because they don't really care about how long it takes to get there, as long as they get there and do the science they need to do. But when you have crew on board, you can't really use that as a consideration, right? Because you can't just say, oh, we're going to take 3 years just to get to Mars, one way, right? It's a non-starter because all the food and everything you have to bring, unless we can figure out how to cryo freeze people, I guess. That would be a different ball game.
Yeah. Wow. I mean, that's one of the key elements here. We're talking about sending humans to Mars, and that with that, one of the requirements is speed.
Yeah.
You need to get there faster.
You need to get there, in a reasonable amount of time before all your consumables and things like that run out, right? Or you have to bring in so much that you never ever even get started, right?
Yeah.
And so that's always the challenge, right? Because with exploring, I always used kind of the analogy of Christopher Columbus sailing across the Atlantic Ocean, right? When they leave, there was no expectation that they have any sort of stoppage and things like that on during the voyage, right? And so they're hoping that fingers crossed that they can get all the way to wherever they're going and maybe resupply. So they are planning, however long they were planning to sail. And at least the good news for us is that at least we know where our destination instead of sailing into the unknown. But to kind of to give you some context, I mean, Columbus sailed in the late 1400s, and they got to I think the first trip they left the Spanish coast and got to I think the Bahamas. That was like 6,500 kilometers worth of distance they traveled across the Atlantic Ocean in like 30 something days. If you use that same distance they travel as if you say, okay, that's the same distance that from Earth to Mars, the moon, which is the furthest humans has ever been, is only 2.5 miles off the coast.
Oh.
So, give you some scale. So, on all human existence, we've only gone 2.5 miles off of the Spanish coast.
Wow.
And we're trying to get across the Atlantic Ocean to the New World.
Yeah.
And trying to plan for that. And so that's kind of gives you that scale. And I think people, think, oh yeah, we because we send probes, and things like that. It should be easy, but it's not at all, because it's one of the most, I think, fundamentally the most challenging thing. That's why we've been looking at it since the Apollo time, right? Because it is that challenging.
Well, tell me a little bit more about what is so challenging about it when it comes to the orbital mechanics of it all, how you're limited with your opportunities, how you can't really turn around.
Yeah, so we are very much governed by what the orbital mechanics and the gravity, and I struggle a lot talking to just people like my family and things like that, like what I do. It's not easy to like have them understand that. So I like to use the train analogy, and imagine like you have miniature train sets or big train sets. I don't know what you want to play with, but Earth and Mars are moving around the sun like they are on train tracks, circular or ellipsoid train tracks, right? So it's spinning around, but they're moving at different speed, right? So your goal of getting from one to the other is you're standing on one of the train track, on one of the trains, moving with the train, and you're trying to throw an egg across and have it land on the other train without it breaking, right? Wow. And so it's not only do you have to like have enough energy to throw it, you also have to have enough energy to slow it down so that when it gets to the train, it doesn't just splatter, right? That's kind of like a basic analogy of how what it would take. So you can think about imagine like if the trains are on opposite ends of the circle, right? They're not in sync, right? You're not going to be able to, you would just take a lot more energy to throw and to slow down, right? And so you're basically what we're doing with Mars in terms of mission opportunities is that we're waiting for the train to kind of align itself to the proper orientations for us to kind of maximize the use of the velocity, the speed of our train, and maximize the speed, on arrival of the Mars train, kind of.
What you're trying to do is you're trying to limit how hard you have to throw this egg.
Right, you have how hard you have to throw there, and you have to limit how hard you have to push back when you get to Mars. I remember seeing. It was a great video that Mythbusters did, where they had a cannon strapped to the back of a truck, and they drove it at 50 miles an hour, and they shot the cannon out the back, and it kind of just fell to the ground.
That one, yeah.
You're basically doing that at Mars, right? And because you want to kind of just like be the same relative velocity, because you're moving fast compared to Mars, right? And you have to fire your engines, fire your rocket and your cannon the other way to kind of slow down and drop at Mars. So you want to minimize that as well, because that's all we call it delta V, the change in velocity, and that drives how much propellant you need. That drives how much your propulsion system has to be in terms of thrust and size and all that, and it kind of snowballs into this giant vehicle that you have to take to Mars. So minimizing that is the goal, right? And that's why we have these very what we call conjunction style trajectory that kind of minimizes that energy.
Okay. So how often do those opportunities come up?
Typically, the Earth to Mars Sonata cycle is about 26 months. So every 26-ish month, you get one of those opportunities. That's why, for JPL, their rovers, they launch every 2-ish years or so. So this one, we have Mars 2020 now coming up this year. The last one was launched in 2018. So that's kind of the cycle that we have. Every 26 months or so, we have these kind of conjunction opportunities.
Now, is there a factor you have to add into this whenever you're looking at these opportunities for the fact that humans are going to be on this vehicle and that you're going to have to return at some point?
Well, yeah, that's always the trick, right? People always think, one way, right? No, we have to it's a round trip. So back to the train analogy, once you get to Mars, in order to minimize the energy coming home, you have to kind of, again, wait for the train to kind of get back into the proper alignment for you to come home. So typically a conjunction style full round trip mission, you're on average about 180 to 260 days, maybe up to 300 days, out to Mars transit time, and you stay on the surface or stay at Mars for 300 to 500 days, waiting for the planet to realign, and then you come home on the same low minimum energy trajectory. So so you have a whole round trip about 3 years is typical, very, very typical. Now with different technology, high and low thrust, those duration do fluctuate here and there a little bit. But typically you're looking at 900 to 1,100 days of total what we call time away from Earth, because that's the days start counting when you push the button to leave Earth. Right? There might be more time the crew has to spend near Earth to they have to launch, they have to get into the spacecraft and get everything checked out before they can even do that. So you have to kind of back that out even further. To get all the total crew time in space, which may be a little more, maybe 100 days more than when the total Mars mission. Some opportunities, mission opportunities are a little shorter. Some are longer because the Earth and Mars orbit are not perfectly circular around the sun, so they do have variations in the distance. So some take a little longer, some's a little faster. So yeah, a lot to kind of. There's just a lot of variability, and we do have to take that into consideration because we've gone into some bad rabbit holes and this mission opportunity is really, really easy. Let's design to that. Well, if you do that, then if you miss it, you can't go ever again, or you can't go for 20 years.
You have to have some flexibility in the design of your systems to meet these different...
And there's one of the things that we harp is we need to be robust with our design, because we understand that whatever we plan, there's always a risk of slippage, like schedule slippage.
Yeah.
And we need to be robust to that. And that's a challenge, right? Because you're already designing a system that is, at the hairy edge of the performance, and you're trying to get everything out of the system you already can, and if you try to build in robustness to that, it's a challenge, because it ends up being really big and bigger than it needs to be for, it's always the, in every system analysis and even aerospace, all aerospace, actually not just aerospace, but engineering in general, there's this debate of robustness versus optimization, right? Optimizing, onto a very, very, being able to optimize to something versus being robust to changes, and then that battle has always been in ongoing. So
yeah, because optimization is equal to efficiency, but robustness is equal to reliability.
Right. Yeah. Exactly. Yeah. And so and there's a balance to that. You can't go full blown one or the other, right? And so yeah, you could theoretically design a vehicle to fly every single mission opportunity, but that's not realistic, right? Because you will be so unoptimized for every single opportunity that you end up with a system that doesn't necessarily closes from a other programmatic perspective, right?
What a challenge! My gosh.
Yeah.
What about launch opportunities? Launch slips happen all the time.
Right.
It's just a regular part of space flight.
And so that is the other challenge, and that we talked a little bit about. The additional time that you need to account for, right? So, so if your launch, your Earth departure date, right, is certain, to maximize your mission opportunity, you gotta plan for the launch slippage, right? So instead of saying, okay, the crew is launching 3 days before that Earth departure date, you're gonna have to plan to launch your crew a month, 2 months before that. That way, if it slips, you can have that. And we have some folks in the agency who's done some fantastic work on launch reliability, and they've done some great analysis to show, in order to get to a 99% probability of actually getting you to this particular date, you have to backtrack and figure out how many days you need to plan to launch, the launch window basically.
Yeah.
So it's a little different than like saying going to the ISS or even back then the Apollo program where a little slippage you end up you can. The lunar cycle is only 28 days, right? And so if you miss that magical opportunity, it's you wait a month and then you go. It's not you wait 28 months or 26 months, right? And so you have to be robust in that, but there's a limit to that, right? And because you don't want to say, okay, we're launching our crew 6 months in advance, and they sit around in orbit waiting for their opportunity to go. Right. And that's unrealistic. So it's again back to the optimized versus robust. This is the risk versus how risky you want to be. Right. Is a 99th percentile probability good enough? Is 90th? Is 70th? I don't know. Right. That's something that it's a challenge for both engineers and the program managers to understand the risk and understand where we can absorb the risk and where we can't.
Yeah. So what you're doing is you're thinking about this wide spectrum of possibilities. You're thinking about how early do we have to launch, and how long is it reasonable for the crew to hang out in low Earth orbit until they take that Mars injection burn and go to Mars. What's reasonable there? What are the propulsion technologies that we can consider, and what factors, into that kind of design? You're just thinking about this whole range right now.
And it's an integrated system and campaign look, right? And that's more so than just doing like the individual design for systems. And the other, throw you another wrench is that the longer you wait in orbit, the more your systems degrade. You might have propellant which are cryogenically, we're at cryogenic temperatures, so they might be boiling off. So you have to top it off. And there's a whole host of discussions on that, and that's why there's some discussion about different orbits where you do your aggregation, different orbits where you do your rendezvous and things like that, so that it's not low Earth orbit is great because you can throw a lot of stuff into it from a launch vehicle perspective because it's lower, but it's a terrible environment for a spacecraft to hang out long term, especially big spacecraft. All right, the thermal environment is pretty harsh from all of the radiation from coming actually reflecting off the Earth from a thermal perspective is not great, but it's also a lot of orbital debris because all the stuff that's up there, so there's a higher chance of that. The benefit is that you're still in the radiation, Van Allen radiation belt, so you're shielded from that. So there's a trade. If you want to go higher orbit, which is sometimes our preference because you can get out of the thermal environment, you can get out of the orbital debris environment, but you take the hit on the radiation for some of your system. But the benefit is that since we're designing a system to go to Mars, all of that system has to be radiation rated and protected anyway, so it's not a huge issue, with the exception of solar panels, which do degrade in radiation environment. So you don't want that to sit in that radiation environment for too long, or else it degrades so that you can't generate enough power.
So where are some of those higher orbits that we're considering?
What we've been talking a lot about orbits around the moon. Orbits around the moon. The Artemis program is with the Gateway is out there in a near rectilinear halo orbit around the moon. We have these Lagrangian points that a lot of folks are very interested in understanding, and what those points really are is if you think about from gravity, pulling each other. The Earth and the Moon are in a gravitational pull system. So the Lagrangian points are just points in the Earth-Moon system that the gravity between the Earth and the Moon is relatively equal. So you're not really being pulled by the Earth. You're being pulled by Earth and the Moon roughly equally. And so those are points that are of interest because it's once you get into those points, it's easy to kind of get out of them. And so if you have a bunch of stuff stacked there, it doesn't cost a lot of energy for it to go out, leave that orbit again to go somewhere else. And so it's great for aggregating a lot of things. And so for what we've been looking at the last couple of years, with the assumption is always that we would launch all of our elements and components into that, kind of like we just call it cislunar orbit, a lunar orbit, just to be generic, because we haven't really picked a particular orbit that we want to be in. It could be the same one that the Gateway is at. That way we can have some synergy with that program.
Right.
But we aggregate all that stuff there. But for Earth departure, you don't really want to depart from that particular orbit, because you do
rectilinear halo orbit. Okay.
Yeah, you don't want to. You could depart from those those Lagrangian orbit, but you get a much more benefit from the Earth gravity if you're leaving from a Earth orbiting orbit. So basically, what you want to do is you want to come back and kind of swing by the Earth on your way out. That would be much more efficient to be able to do that. So the assumption is always we come back to a high Earth orbit, or we call lunar distance high Earth orbit. So it's a big orbit that comes by the Earth, and it comes when it goes out. So the orbits are always defined by a perigee and an apogee. A perigee is the closest to the main body, and apogee is the distance to the furthest away. So your perigee is close to the Earth, but your apogee is actually at lunar distance. So a lot of our trajectory, we actually been doing a lot of analysis and building a lot of these very intricate trajectory for how we do Earth departure, to try to minimize the energy we need. Right? Typically, when you do what we call the trans-Mars injection burn, so burning for Mars, you come by Earth and you fire on your rocket engine and you burn really hard and you kick out there. Which is great and it's fast, but it takes a lot of energy, it takes a lot of propellant. So we were, when designing our hybrid low and high thrust combination type of propulsion system, we're trying to minimize how much of that chemical burn that we have to do. So we designed up these pretty intricate trajectories in which we come back into this high Earth orbit where the apogee is at lunar distance, and we phase it so that after the crew gets on board the spacecraft, we target the moon, we do a lunar flyby, and that kicks us out to heliocentric space. And then that gives us enough energy to come out. And this only really works for the hybrid, because technically once you get flung out by the moon, you don't have enough energy to get to Mars yet. But with the low thrust, you can then use the time you have in space to thrust and to kind of keep pushing and pushing harder and harder for you to catch up to Mars.
Okay, so this moon slingshot thing works only if you have the solar electric propulsion.
Electric propulsion
give
system.
You the extra boost.
So and because or else you this orbit, if you just slingshot around doing, you don't have any more propulsion, you eventually fall back into Earth, and maybe a year later you catch back on Earth again. But so you go on a little tour of the Earth orbits area, but you're not really going anywhere in particular. So.
Yeah, so that it brings up a good point. So let's say for whatever reason you do that Mars or that moon slingshot, but your solar electric propulsion doesn't kick in. Now you got to swing back. You're hanging out in space for a year until you get back.
Yeah, that's always the challenge, right? People, this quote unquote abort. I think people, not their fault. Like when people say abort, everybody have a good understanding of what that is, right? Because we have all these abort scenarios, like, you're coming back home pretty quickly, and things like that. But yeah, man, when you're in heliocentric space, it's not that simple. It takes a lot of energy to come to quote unquote turn around and burn home. For your kind of like a low thrust, if you just do a lunar gravity assist, let's say in your scenario your electric propulsion system just craps out and doesn't do anything. The benefit is that you still have your chemical propulsion system, so you could theoretically, and in terms of your orbital energy, you're not that far from Earth. So we haven't really done the analysis to understand how quickly you can get back. That's really, really dependent on the orbit, the particular date you're looking at, and things like that. But we do have some analysis done on the high thrust side of things. After you do your big burn, can you, I guess in those scenarios, it's like, oh, if a crew has some issues, they need to come home. What are the options, right? And honestly, it's pretty limited. Even with like, this is one of the benefits of people have touted for the nuclear thermal propulsion system, which is kind of like it's kind of like the chemical, but instead of combustion in the using the propellant, you're using a nuclear reactor to heat up the fuel and expend it out. So it has a higher specific impulse, but you have to carry a nuclear reactor around, which
has its own
challenges.
Yeah.
But they talk about these abort scenarios because it has the efficiency that the chemical system doesn't have, but that's still, once you kick out, and especially those high thrust trajectory, you're on much higher energy. So in order for you to turn around and burn back towards Earth, it's not a straight shot. It's not like me doing a U-turn and coming home. There's no U-turn really to be done. You almost have to burn enough so that you fly by, you do a really close swing by of the sun and come back and catch back up on Earth with Earth again, and that could take a year or so, or 6 months, depending on when that burn happens. So the challenge we've always had when these type of questions come up is, in what scenario do you have a crew crew health situation where the full Mars mission 3 years round trip is not acceptable, but a 6 months, 1 year return is acceptable, right? What scenario you're thinking about? Because I don't know what the scenario is, right?
Yeah.
And so that's I think that it's important to have that discussion because we need to understand where these questions are coming from and the people's concerns about all this, and understanding like the scenarios in which they want to protect for. And this is again back to the risk thing, right? If we want to protect for certain scenarios, we can run the analysis to show what it would cost, right? And then it's up to the decision maker to weigh the cost benefit analysis. Say, do we want to protect for this or not? What are the probability of this actually happening? And we, from a system analysis perspective, need to show, okay, if you want to protect for this risk, here are the implication and how that system change impacts the rest of the other systems that are related, right?
Yeah.
So
This goes back to what you're thinking about, which is this wide range of possibilities when you're thinking about propulsion technology, when you're thinking about possible trajectories and the orbital mechanics of it all, how to design a mission profile, however long it may be. That's they're all worthy discussions to have, but I think really what it comes down to is a mission to Mars is a risk. Like you can't make it risk free. That's just
absolutely.
That would be amazing, but it's just not the way it is.
Yeah. It's like going skydiving, right? There's some inherent risk in that, and there's nothing you can do to remove all the risk, right? And so we can sit here and talk about, and engineer and design system to be as risk free as possible, but it will not be 0% risk, right? I mean, inherently, just getting on the rocket and going into space is probably the riskiest part of, could be one of the riskiest part of the whole endeavor, right? And so at some point we have to be willing to take risk, right? And I think one of the challenges we have as an agency, especially when it comes to the Mars program, is that number one, it's so challenging, right? We've kind of established how difficult it is. So we need to have these hard discussions about risk and cost and schedule and programmatics and things like that. But it's also double challenging because it's so far away always, it seems like, right? And it's hard to make decisions now, the hard decisions that, might not have impact for 10, 15 years down the road.
Let's talk about the moon to Mars, what we're striving for right now.
Yep.
You already mentioned a little bit about the Artemis program and what we can learn about the near rectilinear halo orbit and some of the technologies needed for Gateway. What will that help inform when it comes to some of these propulsion technologies and some of the ways that we're thinking about how the moon can help us get to Mars?
Yeah, from a propulsion perspective, that's one of the benefit, right? We're for the what we've been looking at the SubChem hybrid is that the electric propulsion thrusters that we are planning on potentially using for Mars transit is being planned for the Gateway as well, right? And so there is some synergy there, and there's some, obviously will be some challenges with the development cycle because the power level is totally different, right? But there's, you kind of draw a little family tree back up to that particular design. I think the big thing for the Artemis program is kind of how the private-public partnership is kind of unfolding in front of our eyes. I think getting kind of the framework for this private-public partnership, as part of the Artemis program, understanding how we can leverage a lot of things that are happening in the industry, in the private sector, can really inform and really drive how we think about designing the mission and think about how we either procure or leverage all the things that are happening. And obviously the private industry have quite different objectives compared to what the government and NASA wants to do. We want to explore, we want to expand our knowledge and really drive and push the technological boundaries. And so that part has to be the forefront of what we try to plan for, and I think we are. But I think the industry, in terms of their push for innovation in areas that the governments might not be interested in, is also very beneficial because they are very interested in streamlining the manufacturing process, being more efficient with their design cycle, and how robust their systems are and the way they do their testing.
There's a lot we can learn from the commercial way of operating things
by
implementing a commercial partnership.
Yeah, just having synergy with a lot of things they're doing and leveraging some of the stuff they're having just dialogue and just understanding how they're doing their business model, if you want to call it, and how we can learn from that, right? And change the way we were doing testing and doing development and things like that. In all industry and in tech in particular, you need to have these kind of breakthrough and these industry kind of like breaking, moments, right? And to kind of drive us out of these kind of complacency that we're in. And at some point we got to decide, we want to go to Mars, and we want to be able to do certain things, and we just have to, push for it.
Yeah. So it's that there is a balance, I feel, between innovation, trying new things and doing things a certain way, and maybe the tradition does have a certain benefit of precedence.
It
informs what is possible because we've
as
done
long
stuff.
as we learn from our history and we learn from the mistakes we've made, right? Struggle with that from every day. To make sure that I think this way. Is it because I'm being informed by data and I'm being informed by good sound analysis, or am I leaning this way because of my inherent bias or inherent perception of a preconceived notion of what the system is, right? And
yeah.
So, and that struggle is real at all levels, and that's something that we have to be kind of very cognizant of.
Yeah. So when you're thinking about solving these problems with team members, finding a way to think efficiently and making sure that you're considering all of these different things, but not getting too bogged down by these decisions. That's a balance just in and of itself. Not just designing these trajectories and thinking about these systems, but coming to a consensus on how to proceed.
Yeah, absolutely. And it's great that we, our branch particularly, have had, every, year or so we get one or two new hires, and we have a bunch of interns that come in. So it's always great when they come in with fresh perspective. They have not been in the mud, making these, trajectories or analysis and things like that. So they come in and say, wait, why did you do it that way? And we go, oh, yeah, why did we do it that way? And we need that, right? Because, you don't want to end up in a kind of a environment in which new people coming in are conforming, they're expected to conform to whatever standard you have. You want them to come in with a fresh mind, with critical view, and to provide us with a different perspective. And that's, I think, the most invaluable thing we have, especially here at NASA, because of our notoriety, and people want to come to work at NASA, and it's a great thing. And we need to keep hiring. We need to keep these people coming in, and young minds, and really get them engaged, not just in school, but before. And so I think a lot of the public outreach things that we do is extremely important. I think NASA is still one of the most sought after thing. People say, "Oh, you work at NASA? That's amazing," and it is. I'm thrilled to go to work every day, and we need that kind of enthusiasm, to continue and the people coming in are they're brilliant. And we need to make sure that we are doing the right thing, and doing things that to make them feel like they're empowered to change the status quo.
Yeah. So thinking about what we've discussed today, thinking about the difficulties of rendezvousing with Mars, and with the different technologies that we're considering, reaching out to those people who want to come work at NASA and fight to innovate and fight to change the way that things are doing. What is a message that you want to send to them?
It is a very exciting time, right? Because we have this whole Moon to Mars enterprise now. The Artemis program is spinning up, and we are going to go to the surface of the moon to do some very exciting science, and with the goal on the horizon of always going to Mars. So these systems that we are developing and partnering with industry partners to develop are going to lay the foundation for what we do at Mars, right? And so it's very important for us to not only do the mission to the moon, but also be very, very cognizant of that these are laying the stepping stone. So we need to learn as much as we can as we do these things to inform all the things that we're going to be planning on doing when we build the spacecraft to go to Mars, right? And so I think it's a very exciting time for NASA.
Well, it's an exciting time, and the future is exciting, because I think every year is just going to be another step closer.
Yeah, and it's like I said, I think throughout this podcast it's a challenging problem, and it is probably one of humanity's greatest challenge. And I think if there's a will, I don't doubt that we can achieve it. But it is a challenge, and we have some of the brightest people on the planet trying to solve it. And it's a great thing, and it's something that I think it's going to be so rewarding for all of humanity. It's one of those, you think about, people talk about, well, what does NASA do besides sending people to space? We do these innovations that we have to develop so that we can send people to Mars. They will have long-lasting effect on our society, and we might not know what that is till years later, but it will. And that's kind of the challenge from a quote-unquote PR perspective, right? What costing X amount of dollars to send people to Mars. So what is that? We could have spent that money here on Earth, but it's like you don't know what you're going to get out of it. But we know that it's going to be impactful, because we have a track record of all the great things that have spun off from NASA technologies that we've came out of the lunar program and the space station program, right? And the Mars program will be an exponential in terms of how challenging it is, right? We're only 2.5 miles off the coast of Spain right now. Yeah. We're going all the way to the to America, right? And so there will, whatever we come up with in terms of solution and technology advancement will be, I think, societal changing.
Yeah. So. Well, I'm glad you're on the team thinking about this, and looking forward to bringing on others to continue it. It's been great work, and this has been a fascinating conversation, Patrick. Thanks so much for coming on.
Thank you very much for having me.
Yeah,
it's been great.
Awesome.
Stop of the space shuttle.
Roger.
Never Houston. Welcome to space.
Hey, thanks for sticking around. Really fascinating conversation we had with rocket scientist extraordinaire Patrick Chai. I hope you've been enjoying some of these Mars Monthly episodes. We started with Michelle Rucker on just the general concept and really the outline of a mission to Mars. Then we explored some concepts near science fiction with Jason Derleth. Patrick Chai takes us into the third month. I hope you're sticking around. We got a lot more episodes coming your way. Again, we're going to do it on the first Fridays of every month, so stay tuned for some of the upcoming episodes. If you liked this episode, or many of the other Mars Monthly episodes of Houston We Have a Podcast, you can find them all at nasa.gov/podcast. You can also check out some of our other episodes. You really don't have to listen to them in any particular order. That's all at nasa.gov/podcasts, as well as the many other podcasts that we have across the whole agency. If you want to talk to us at Houston We Have a Podcast, you can find us at the NASA Johnston Space Center pages of Facebook, Twitter, and Instagram. Just use the hashtag AskNASA on your favorite platform to submit your idea for the show, and make sure to mention us at Houston We Have a Podcast. This episode was recorded on February 4th, 2020. Thanks to Alex Perryman, Pat Ryan, Norm Moran, Belinda Polito, Jennifer Hernandez, and Michelle Rucker. Thanks again to Patrick Chai for taking the time to come on the show. Give us a rating and some feedback on whatever platform you're listening to us on, and tell us how we did. We'll be back next week. Houston, we have a podcast. Welcome to the official podcast of the NASA Johnson Space Center, episode 153, Perseverance. I'm Gary Jordan, and I'll be your host today. On this podcast, we bring in the experts, scientists, engineers, astronauts, all to let you know what's going on in the world of human spaceflight. NASA is paving the way towards a sustainable presence on the Moon and onto Mars. Though humans have never set foot on the red planet, we've been there many times. Most recently, the Mars InSight lander that went to the surface of Mars to understand the planet's quote-unquote vital signs, its seismology and heat flow, and whether the planet's core is solid or liquid. Before that, the Curiosity rover landed on Mars to explore the surface for chemical and mineral evidence of past habitable environments on Mars, searching for environments where microbes could have survived billions of years ago, or these habitable environments. I remember watching Curiosity's landing live, and man, what a thrill. NASA's Jet Propulsion Laboratory is sending a new rover to Mars. It looks a lot like Curiosity, but with a whole new suite of incredible instruments, many of which are in direct preparation for human exploration on Mars. We're talking instruments to test the production of oxygen from the Martian atmosphere, identifying valuable resources such as subsurface water, improving landing techniques, and characterizing Martian weather in a way that could help future astronauts that are living and working in the environment. So here to go into detail on this new Mars 2020 rover called Perseverance is Luther Beagle, Deputy Division Manager for Science at NASA's Jet Propulsion Laboratory. Luther is also the principal investigator of the Sherlock instrument, one of the scientific instruments on Perseverance. Note that this episode was recorded prior to the most recent change to the launch date of Perseverance. For the latest information, please visit nasa.gov. So here we go, the Mars Perseverance rover with Luther Beagle. Enjoy.
T-minus 5 seconds and counting. Mark. Launch commit lights are correct.
Here she goes. Houston, we have a podcast.
Luther Beagle, thank you so much for coming on the podcast today.
Oh, thank you very much for having me. I really appreciate it.
This is a very exciting topic. I love this is a very exciting mission, one of the top priorities for NASA this year, and it's coming up. We're releasing this episode on July 17th. Fingers crossed that we're still looking for that launch date. This is a big mission. I want to start before we dive deep into Perseverance in this mission. I want to start with you. Your interest in astrophysics. You have many degrees in astrophysics, and I want to understand kind of where that all began. Where did this spark something that you wanted to dedicate your career to?
So I think that, like most people, at least in my generation, basically Star Wars had a really big influence on me, not only from the perspective of entertainment, but from the perspective of what could possibly be out there. I'd watched science fiction movies in the past, and I think everybody had grown up wanting to be a spaceman. I've seen this. I'm just old enough to remember one of the last moon missions, and watched movies about Mars and things like that. But when you start thinking about all of the permutations of what could possibly be out in the universe, it's really fascinating. And my interest went beyond just life. It went to what the stars are like and what the planets are like. But I always kept coming back to what was life like, and that's one of the reasons I am where I am.
And that's got to be the genesis of why you pursued physics and astronomy first with a bachelor's, right? Physics is, I mean, I've heard it described as just like the language of the universe.
Yeah, and physics really is why things are the way they are. And a lot of it's problem solving, and I like problem solving. Physics, you're given incomplete information, and you try to figure things out, and it really is, at its very heart, very simple. All of electricity and magnetism really can be boiled down to 4 equations, Maxwell's equations. And then from there, you can build on everything else up there. And I always found that fascinating, that there are things that you can, figure things out with incomplete knowledge. And that was always fascinating from a problem-solving perspective. And it also fed into my interest in astrophysics and astrobiology later on, in that being a problem solver at heart, physics allows you to go into other things and try to solve problems in those fields as well. And it was a fascinating education.
That's got to be where your interest in astrophysics, just understanding how the universe works, how that intersects with Mars, which is really the topic of today, is that's what this Perseverance Rover is going to be doing. We want to understand more about Mars. So how does that intersect, your love of astrophysics and Mars?
Well, so Mars is the closest planet we have, and it's actually the most Earth-like planet. So when we start thinking about where, understanding of where we came from an origin of life and origin of species perspective, Mars is it. Mars, we were close to it. We're able to access it. We're able to go down to the surface and touch it. We can see it. We know what it was like in the past, because you can see evidence all over the surface of different processes that happen. So when you go thinking about looking for life, Mars is the first stepping stone of a lot of that. And it also enables us to try to start thinking for the first time of what actually is life like, and how do we go look for it. Those are questions that have come up a lot over the past 30 years of my career that people have asked, and we continue to talk about them, and that's why Mars is special.
That's a perfect lead into this next topic. You talk about there's evidence all over the surface of this, and it's worth noting that this is not the first time we're going to Mars. We've been to Mars, not exactly humans, but we've sent a lot of things to Mars to investigate that. Give us a brief history of what has been, how we've gone to Mars in the past through various missions.
So Mars is probably the most visited and really understood planet we have other than the Earth. Actually, it is the most visited and understood planet that we have beyond the Earth. We've gone there since space age. We've looked at it through telescopes. We've all heard the stories about the canals of Mars and Percival Lowell and people like that. And we understand that we've been looking at Mars for hundreds of years, and the ancients knew about it. We started sending spacecraft as soon as the space age started. We sent the Mariner spacecraft to Mars. We thought we weren't exactly sure what we were going to see, and when we sent Mariner there, we found a cold, dead planet. There wasn't life on it, like people had assumed there might be in the past. But Mariner did see things like dried riverbeds and other things that could only have been made through water processes. So we started to figure out very quickly from Mariner, the Mariner series, that Mars at one point had to have liquid water on the surface, and now it was no longer possible. So that brought Viking, and Viking was launched in 1976. And the Viking consisted of 2 landers and 2 orbiters. And what Viking did was Viking took a map of the planet. The orbiters took maps of the planets, and the Viking landers went down, landed on the surface, scooped up some material, and tried to see if there was actual life associated with them. And we learned a lot from those experiments. We learned, one, you really have to understand the geology and chemistry before you do a biology experiment, which was a big deal at the time. But we also learned how to operate on another planet, which was very important. From there wasn't anything on Mars till 1996, when we launched Pathfinder, which was a small rover and a lander, a Met Station lander. That was the first time we'd roved on another planet other than the moon. Pathfinder went out and looked at a big giant rock to try to get the elemental abundance of that rock. From there, the 2003 mission, the Mars Exploration Rover mission, sent Spirit and Opportunity. These really were two field robotic geologists. And what their job was to go out and understand the geology of Mars. So one of the things we learned from Viking is when Viking tried to do the biology experiment, it came up with a result that we weren't 100% sure what to make of it. Some people thought it indicated there was life there. The vast majority of people thought it was just a chemical reaction. But what we learned is that we had to really understand geology, we had to understand chemistry in order to understand biology. And so Spirit and Opportunity were two missions that went there to two different locations and started looking at the geology. Let's understand the geology. And what they found a planet. They found minerals, and they found environments that were aqueous in nature, so that there was liquid water at both those landing sites at some time in the past. And that's important because now we know that Mars, we can see different places on Mars that all had these same aqueous process associated with it. We sent Mars Reconnaissance Orbiter in 2005. That was taking high-resolution images of the planet and did some spectroscopy of the planet as well, so that we can understand from orbit where different mineral deposits were. We've sent Maven. That was a scout mission, and InSight. They were two smaller class missions to look for whether Mars had earthquakes. That was InSight. Maven was looking at the atmosphere, trying to understand what happened to the atmosphere. We know Mars' atmosphere now can't support liquid water on the surface, but we know in the past it had liquid water on the surface. So what Maven did was Maven tried to figure out what happened to that atmosphere and what were the processes that moved forward with that, which was really cool. And then Curiosity, which was the biggest rover we had sent to date in 2000. It landed in 2012, and that really was looking at chemistry. And looking for organic molecules and trying to determine whether the planet was habitable in the past. And by that, we mean whether or not there conditions existed on the surface of Mars that life as we know it could exist. And Curiosity has found that at Gale Crater. And that's pretty much the history. So that leaves us to Perseverance, which is going to go do basically look for potential biosignatures and try to cache samples to return to Earth later on.
Yeah, that's a huge milestone and a difference really with Perseverance. You went through this beautiful history of all these different rovers and landers and orbiters. I mean, we've been sending all these crazy instruments to really, as you said, this is the most studied planet other than Earth, and you can see why. I mean, we're looking at all these different elements that are really diving deep into the history, how this planet works, what's on it, the history of it. It's absolutely fascinating, and it sounds like Perseverance is just taking those next steps.
Yeah, if you look, there's been a thought process for the whole program, right? It's not just let's go send a biology mission, and a very complicated biology mission, but we're going to build blocks. We're going to understand this. We're going to understand that. We're going to understand, geology, then chemistry, then understand the internal dynamics of the planet, understand some of the history of the planet, and we build along the way. So and we look at different sites along the way as well. So what happens is that you start adding all of these things together, and then what you're left with is a really interesting history of the planet and a better understanding of the planet.
Wonderful. Well, let's dive into Perseverance, because you ended when you were going through this history of the different orbiters, landers, rovers, all those. You talked about Curiosity. I understand a lot of Perseverance is modeled after Curiosity. In fact, if you look at pictures of the two of them, they look very similar.
They do. MSL Mars Curiosity is a rover that's about 900 kilograms. It's about the size of a Mini Cooper. It has a scientific payload that's very complex. Perseverance is more complex than Curiosity in several ways, but it is built on this. The nuts and bolts and skeletons are the same from Perseverance as they are Curiosity. So whenever we go do a new mission, we have to learn from scratch how to do a lot of things. For example, the wheels, how the wheels work, how tools interact, how the robotic arm interacts. So what we did with Perseverance is we took all of the stuff we learned from MSL and all of the stuff we learned from MER and added to it to make a more complex mission. But we use the same type of skeleton to actually do this. So from the outside, it looks the same. It has 6 wheels. The wheels are very large. I think they're 65 centimeters in diameter. It has a robotic arm. It has a mast. The mast looks kind of the same. The robotic arm kind of looks the same, except it's much more complicated. So our robotic arm on Perseverance is much bigger than the robotic arm, and it's much more capable than the robotic arm on MSL. But we had to learn how to do all of that with MSL so that we can go to the next step and learn on what we're doing on Perseverance. The other thing Perseverance has that MSL did not have is we have the capability of caching samples. So the robotic arm has a core on it, and that core will go out to different spots that we decide to pick, depending on the diversity of sites and things like that and how much scientifically interesting the sample is. And we will basically be able to capture some of that sample, put it in the tube, seal that tube up, and then basically go back and pick it up later with a different mission. And so Perseverance does the science, my instrument Sherlock, Pixel, SuperCam, MassCam, C, RimFax, and Moxie, and Meta. We all are doing great science to characterize the sample, and then we're going to be able to bring that sample back. So that's the next step in Mars exploration, is the sample return aspect of this particular mission.
That's perfect. That's one of the new objectives of Perseverance. But what I'm hearing with this skeleton, the framework that you were talking about, it sounds like it's just what Curiosity did beyond its own scientific missions was prove that the hardware was working. It had to do with maybe a sense of that this technology, the way that you rove across the surface of Mars was proven, and then you just take the different scientific instruments and objectives you want to do and rove across the Martian surface, just meeting those objectives. Is that the idea?
That is the idea. And what happens is that you have it's a learning process the entire way. You had to learn to walk before you could run. You had to run before you could fly. And that's exactly what we're doing here. I used to work on Curiosity, and I was part of we called ourselves the surface sampling system scientists. And what we did is we tried to figure out whether it was possible to drill on Mars and what type of materials could you drill into, could you not drill into, because this is all stuff we've done for the very first time. And it's really scary because you send something to Mars, if it breaks, it breaks. There's no way to fix it. There's nobody duct tape with a spacecraft we used to joke about all the time that could just basically take themselves off, fix the hardware, and then just basically go back on. You're stuck with what you have. And so you're really, really trying to figure things out along the way. And by learning all of these things, learning how the rover operates in this particular environment, a sand environment versus a rock environment, now we understand all of that. We can design things better. One of the things that MSL did do is we had a wheel issue at a certain point. We realized that the wheels were degrading faster than they were designed to. So we learned from that, and Perseverance has a new set of wheels. And you could only do that by doing the in situ testing of that. We understood how the robotic arm placement can be. So how do we put a drill down, whether the drill interacts with the rest of the rover in a bad way. So now we can do a core, which is a more complicated piece of equipment. So you keep learning along the way, and you keep becoming more and more sophisticated. I think that MSO is the most complicated mission ever flown, a robotic mission ever flown, and Perseverance is more complicated than that. So we keep adding and we keep getting better, which is what we in NASA tend to want to do, is always push the envelope.
That's incredible. Yeah, there's been a lot of strides, and I could totally see the logic of wanting to. It's the ultimate test, right? Those wheels on Mars. It's the ultimate test for the wheels. You learn from them and you make them better for the next mission. It's perfect. Talk about some of the just general design features of, I guess, a little bit of curiosity, a little bit of perseverance, things that make this the right type of rover. I know. Just I was really into Curiosity in 2012 with the landing. It was just such a big event for me, and I was really fascinated by the wheels and just this trade-off of torque and speed and wanting to get over some of those rocks and stuff like that. So some of those engineering design elements of how Perseverance will do the roving on Mars.
So the way Perseverance is going to do it is much like Curiosity did, with some added exceptions, which I'm not 100% sure are actually going to work. Not work, but be implemented, because working is a different concept. We have the large wheels, and what the large wheels enable you to do is not worry about the number of. It really reduces the number of hazards in a particular site. As you get closer to the ground, bigger rocks become problematic. If anybody's ever driven a Jeep versus a car that's very low to the ground, you'll know that if you go over a speed bump, you kind of sometimes scrape against the ground. By having the bigger wheels than MER did, you're able to go over a lot more of those particular rocks and not have to worry about them. They become less of a problem. We've learned on Curiosity, we had problems at Dingo Gap of getting over sand, getting up and over a sand patch. So we kind of understand that we can't get over that. Those wheels, we learned how to drive backwards to save wheels on MSL that we will learn on Curiosity. Perseverance. The wheels themselves, we go actually relatively slow. I'm not sure what the speed limit is, but we end up going on Curiosity 80 to 100 meters a day. I think is an average, is a good day for Curiosity, and hopefully we'll be able to push that a little bit on Perseverance. We have a proven landing system on Perseverance. We're using the Sky Crane, the exact same design as we used on Curiosity. Hopefully that will enable us to get to within a smaller and smaller place of where we want to go on the ground. So what happens is that the original landing systems had a landing ellipse, which is basically where you land, that were very large, hundreds of kilometers. We've now lowered that down into the tens of kilometers range because the landing systems have become better and better and better. And if you're going to send humans, you really need to even reduce that even further. But the landing system now has enabled us to go to Jezero Crater, which we would not have been able to go under old landing systems because it's too hazardous. But we've reduced the error, where we can land greatly. And we use a lot of the same parts to do that. It's been the design is solid and been tested, so it enables us to take a little, go to do things that we haven't been able to do before.
So this is just to confirm, this is the same landing system, but it sounds like was there a few upgrades to make it a little bit more precise too?
There is a different feature on this landing system called terrain navigation.
Cool.
And so what we're able to do is we're able to, when we go down through and we're in the final stage of descent, the rover has on board images of what the landing ellipse looks like, and it can tell whether it's in a spot where this might not be the best place to land us, so let's move over a little bit. And that's a new feature with this rover that we didn't have on the last one. The last one, we could go down and lower everything down to the surface, and landing on all four wheels or six wheels and just move off. This one allows us to go to a spot that we wouldn't have been able to go because we have the terrain. We're able to avoid terrain that we can't get to in the past. The EDL system operates, you go in it's about 17,000 miles an hour when you get the top of the atmosphere, and 7 minutes later, you've got to be going 0 miles an hour. There's a great video online of describing this called the 7 Minutes of Terror that describes the entire EDL system, and it's all automated, and it happens we just turn it on and we let it go, and we find out whether or not we landed or not. But it's the Sky Crane configuration. we hit the top of the atmosphere going 17,000 miles an hour. There's a heat shield. That heat shield dissipates heat in the atmosphere. It slows us down to, I'm not sure what the miles an hour is, but we then lose the heat shield and we open up a parachute. That's a supersonic parachute. It's a very large parachute, which then dumps more energy. We slow down even further. But we get to about a couple of kilometers above the surface, and then we're on retro rockets. So the landing system itself takes over this active landing system. And the sky crane itself, it's kind of like the landing system is all over the rover, and basically the rover gets lowered to the ground by a rope. And then the rover hits the ground and then moves off on its own power. It's really cool to watch. It's a really cool video to see how it all works.
I loved that video, 7 Minutes of Terror, especially back in 2012 when I was following Curiosity. I watched that over and over and over. It was just fascinating. Is this landing system the one you're describing for Perseverance? Are there elements of this? Because I know when I was reading the description of Perseverance and some of its objectives, one of the things was improving the techniques for landing. Is this one of those things that might actually help us, the landing of Perseverance might actually help us understand how eventually to land humans on Mars?
The answer to that question is I don't really know. I do know what it does do is it's completely instrumented. And so it understands the nature of the Martian atmosphere better. And by that, we can design better landing systems. I think there's probably an upper limit to how much this landing system can land. In fact, I know there is because I've read some of the mission architectures for potential humans to Mars. And so they all have different landing systems associated with it. But this gives us information on what that atmosphere is like in the higher above the surface. And so we can take that information and design better systems. And that's the important part of the EDL system for eventual humans to Mars. I don't know whether or not this scales to full human activities. And that's a lot more mass.
Yeah, sure. Not necessarily design, but understanding what the environment is that you're dealing with. That's gotta help for sure.
Yeah, it does, and it basically flows all into that. And we every time we land, we learn something new, and it's good.
Perfect. You mentioned some supersonic parachutes. There's a lot of crazy engineering that's going into the landing here, and I know just from curiosity, a lot of it is familiar to me. But for Perseverance specifically, some of the development and testing of some of those things to make sure Perseverance is going to survive the journey.
Yeah, testing is we joke all the time that testing is always nerve-wracking because you've spent 4 years building something, and then all of a sudden you go in to test it, and you just hope that it works the way everything is supposed to work, because it really puts the needle to the test. There's a better description than that. So what happens is that we had to test everything. And so if you remember back to what I was talking about with the Mars exploration rovers, everybody talks about the fact that they were only supposed to exist for 90 days. But really what that means is that all of the instruments and all of the hardware were tested out to about 3 times life. So we test, and we test for 3 times what the eventual life is going to be. We don't test things till they die. We test things to make sure that they work for 3 times what the nominal lifetime is. And what that means is that Mars is a very difficult place. Mars, every day on Mars, the temperature swings are about 100 degrees centigrade, which is about 200 degrees Fahrenheit. So imagine going from ice freezing to boiling, freezing to boiling, freezing to boiling every single day. And all of the hardware has to work through those environments. It's also a very, very dusty place. There's dust gets into everything. You can see pictures of Curiosity